Hello.
Hi, Digam.
Yeah, hi.
Okay, Lucky, you can start.
Yes. So, good morning, everyone. I'll be presenting today the paper Verification of Camera-Based Autonomous Systems by Habib D'Souza, Todia, Prabhakar, and Deka. So, here's the introduction. So, why do we need self-driving stuff? So that it can make life easier for everyone. It can also uh, include economic benefits like automated delivering services and all. So, many of these neural networks are used in these self-driving models to uh, predict the trajectories of the system. So it is expensive to test and train models in real-world environments. So therefore, we use 3D simulation to model and solve such problems. So in this paper, we consider the problem of verifying the safety of trajectories of a camera-based autonomous vehicle in a given 3D scene. That is, we'll be checking whether the trajectories given by the neural networks are safe or not. Safe means it doesn't cause any harm. I'll be describing everything in the following slides. So let's start with the environment. Like I said, we won't be actually dealing with the real world environment. We'll be treating everything in terms of synthetic environment. That is a 3D scene which contains triangles, which are our obstacles. It also contains our vehicles. It contains the initial region and the target region. And our vehicle will start from any point in the target region and will proceed avoiding any obstacles and try to reach the target positions using the neural network. So this is the autonomous vehicle model. What it does, it takes the 3D scene E. It has a camera which takes the input as an image. It feeds that to the neural network.
Okay, Lucky, sorry to stop you. Can you go to the previous slide?
Yes, sir.
Yes. So, it's a 3D scene is a three tuple. There are vertices.
Yes, sir. Triangles are the set of obstacles.
And there are vertices and TR set of triangles.
Yes,
What are the vertices? I mean, the vertices are the ones of the triangles. That's what.
yes, sir.
Huh?
Yes, sir. Yes, sir. Yes, sir.
And what is colored here? The vertices are colored or the triangles are colored?
So technically, the vertices are colored, but when we project the image, when we make the image, the colors of the vertices are used to flood the entire triangle, so that I can generate an image consisting of colored triangles.
Okay, so the scene is actually a bunch of colored triangles. That's what it is. And some of them, okay. So, okay, yeah. So there's no connection between the triangles. They're just a bunch of triangles in a 3D space. That
Yes,
is
sir.
what
So
the
technically,
visualization that is captured by.
yes. So
Uh,
technically, any
yeah,
world.
yeah.
So
No, I
technically,
mean there are the triangles can overlap with each other to build some object,
yeah,
right?
yeah, they can form complex polyhedron shapes and all using connections and intersect each other.
Yeah, but I mean, at least your model does not show connections, does it?
I mean, I can just make triangles. I mean, I can just put this here and there. So
Can you show that? Do you have that particular image from the paper somewhere where they are showing the environments?
Yes, sir. I'll be coming to that.
Okay, fine.
Okay.
I mean, this is just the introduction.
Deepro was saying that your voice is breaking.
Hello,
I
hello.
can hear you clearly. Okay, I don't know if it's
Yeah, I'm also able to hear clearly.
yeah, let's continue. It's fine, he says, Deepro. So continue.
So here's my autonomous vehicle model. What it does is it takes the image from the 3D scene, it feeds that to the neural network. It gives the control input U using this controller M. I'll come to this in the implementation part. And using all these, it predicts a new position of the vehicle. So now I'll be assuming from now onwards that the vehicle has no volume and it can only look at a plane parallel to the x-axis. that is, it does not support rotation and all. Also, I'll be starting my vehicle from an initial region I and try to end up at some target region T, at the same time avoiding obstacles in the sea. So here's the image which you all wanted. So something like this.
No, can you go back to the previous slide? So what is the significance of the target region? You went too fast. Okay,
Target region is a set of points where I'd like my vehicle to reach by the end of my journey.
Without actually avoiding the obstacles.
Yes.
Okay.
Yes. So this is how my image will look like from the camera. Also, I won't be going into the details of this image generation right now. I'll be dealing with it later in the slides. So just assume for now that this is something like this is being generated at the canvas of the camera. I mean, my neural network can get an image like this, but the image I get will be sort of pixelated. I'll come to that soon. Like this. So my neural network will see a 9x9 grid of triangles. So this is the image my camera, the vehicle will see. Is this all right? And I call this image C in the given environment E at point P. P is my position of the camera. So now, this is the visualization of a vehicle trajectory. I start from some point in initial region, this thing. I call that position zeta t naught. I mean the starting time stamp, the time unit. And then in the next interval, my camera looks at the image formed here. It decides where to go next, and then it goes there. Now at time zeta t1, that is the next time stamp, it goes to this position. Now it goes here, it goes here, it goes here, and it goes there in the target region, and then it ends. So this is one safe trajectory because it avoids every triangles in the scene. And then, so the formula of state, the state is the 3D coordinates of the model, the current 3D coordinates of the model. The formula is this: zeta I t plus t equals to this. So it is the current coordinates of the model, and then at t I use the image generated at the point. I feed that to the neural network. I get this u. I multiply by that t. The t means the whatever interval I'd like to generate my position of, and then I do this and I get the next position of the my vehicle model.
So why multiply by t there? Why should you multiply by t?
For example, t. This is just the. I mean, they have used this notation. For example, if I'd like my vehicle position in the next time interval, I'll set this as 1 tau. Tau is the one time unit. So it's like just scalar multiplication and addition. It's nothing special. I mean, they are just using this notation. I mean, they have trained the model using this only. So
there's some kind of normalization of the position or something. I mean,
no, I don't think so. It's being done right now. I mean, normalization is done, but at the end using the controller matrix. I mean, to get this thing, this u. U is the direction vector. You can think of it as a direction vector of this. So I multiply it by some time interval. I get the vector
some
position.
distance by which it moves.
Yes.
And that is based on the time. And that's why probably. Yes. Okay, got it. Yeah.
And then, so I'll be now introducing you to the reach avoid problem. So the problem statement states that given an autonomous vehicle V equals to C N M tau. So C here is the canvas height in pixels, width in pixels, and height in meters and width in meters. So the image I showed you was the pixels, the grid pixels and all. It's contained in this C. Also, N is the neural network. Are you guys here?
Yeah. Go ahead.
And M is the controller matrix. I'll be talking about this in the end. It's just the implementation part. It is used to scale this vehicle model to, I mean, different types of vehicles, for example, cars and all. And tau is one time unit. So also I'm given one 3D scene E. I'm given an initial region I. It is a set of points from where my vehicle should start. Also, I'm given a target region T. It is the target, I mean, the set of points where I'd like my vehicle to reach without crashing or colliding with any obstacles in this. So this is the definition of a safe trajectory. The verification problem we'll be dealing is to, given such a autonomous vehicles, CE, I, and T, I'd like that all my trajectories predicted by this neural network are safe. And safe is that it does not collide with any obstacles. So now, to deal with this problem, the paper suggests, or I mean derives 3 algorithms. So there are 2 algorithms, algorithm 1, 2, and there is one falsification algorithm. 1 and 2 are verification algorithms, and 3 is a falsification algorithm. So that means that algorithm 1 and 2 will be verifying every trajectory the neural network can take. And if every trajectory is safe, then it will return safe. Otherwise, it will return false. Algorithm 3 will just give a counter example. If it does not give a counter example, doesn't mean that there does not exist this thing, unsafe trajectory, given a timeout. So they have implemented all these algorithms in a tool called AirVerif. So one naive algorithm one can think is that why cannot we iterate over all trajectories? I mean, I've been given a set of points, so why can't I just try to find every such trajectories and see if that is safe or not? That does not work because there are possibly infinite number of points in the initial region alone. So I cannot implement any DFS sort of algorithm because the search space is infinite. So now, what if we reduce the search space to some finite domain? So here comes
just pause here.
Yes,
If anybody has any question about the overall system that is being verified, the block diagram and the problem the verification problem that Lucky has defined. Okay, before he moves into more details about the algorithms.
Is enumerating all trajectories like practically infeasible, or is it like theoretically just
it is infeasible because I mean there are like infinitely many points where you can start from. So there are like infinitely many.
Right? Initial
Yeah. So the 3D space is like R cube. I mean real number cube. So there are like infinite real numbers.
No, I was thinking like in like a SAT solver does somehow.
Oh yeah. I mean it can. That's nice.
Sure.
Yeah, that's a good question. I guess, Shobit, I mean, what you mean is, can you elaborate? I guess if you could, just like abstract interpretation, the region can itself be modeled as a polyhedra, and then can you propagate those things? I think that was his question.
I think that should be possible, but this paper does not deal. I look at this problem with that respect because I think solving such a problem using this might take a lot of time. I mean, we are trying to create we are trying to implement an algorithm which works in critical systems, and therefore, and also has a timeout thing. I mean, it cannot be working infinitely. And so I think modeling such a problem in us using constraints and all, and solving it using some simplex solver is like infeasible because it might take a lot of time.
But is that not what we're doing ultimately?
Yeah, in the abstraction method, that's the question I had as well.
We are doing that, but not in like the general case. Like I can just formulate the entire thing in this thing that I can formulate the notion of a trajectory, and then I can try to find a trajectory which does not collide with something like that. I can do that, but that will be a lot of work for the solver alone. So I am trying to reduce that the overhead on the solver.
Okay, so maybe this is a question for later on,
Yeah.
but I still don't understand the distinction between what is perhaps being done in the paper and what you're referring to when you're saying that, okay, I can model it in terms of constraints. I mean, one way to do that would perhaps be what is already been done, but let's take this up once the actual paper has been presented, maybe.
Okay. So now safety checking algorithm. So this is the first algorithm which the verification algorithm which the paper tells
So,
about.
by the way,
Yes.
Lucky, there was
Yes,
there is a picture in the paper with a road and a bunch of obstacles and so
yes,
on.
sir. Yes, that's in the experiments part.
Yeah, can you just maybe show that once, because then it will be clear what the environment is. It's not too much of a trouble.
Yes.
Yeah, we see. Yeah, so this is the environment made of triangles, right?
Now, what about this picture? What do
No,
we?
so I'm just saying that. So you had the question about, are the triangles connected and are they intersecting?
Ah,
So for example, this is entirely made of such triangles. So it's got some road, it's got some trees, and so on. Uh, yeah, but it's entirely made of triangles, and now there is some initial and some final region which is not shown here. But in any case, the vehicle needs to navigate through this.
So there's some overlap. Okay, this is kind of projected onto a plane, but it's actually in 3D. So I mean, its trajectory is in 3D. So although
Yeah.
there seems to be overlap, there could be paths in between those triangles and so on, I presume,
Correct. Yeah,
that
yeah, yeah, yeah.
navigate through those things.
Yeah. So for example, this white like marker in the middle could be a path that you can just navigate along.
Hmm. But my question was, I guess they don't need any connection. Okay, they don't
Yeah,
need
all of this will work just
Yeah.
if you have a set of triangles. I mean, it doesn't really
triangles.
matter where they're connected. Yeah.
Hmm.
But yeah, I think this picture would sort of concretize what we were talking about.
Yeah, but this one, what is shown here is the output of the camera or on the canvas, or is it the actual 3D image? I mean, projected onto a plane. What is this?
No, it's. I mean, both. I mean, both are the same thing, right? Like if you look at the scene from any one particular point,
That's
what
right.
you'd
That's
get
right.
is what the
Okay.
camera would see.
Yeah,
Sorry.
yes, you're right. You're right. Okay, this is yeah. I mean, I
Yeah,
was
sorry. I think we are hijacking your presentation too much.
yeah, okay. Yes, okay.
But also I think the image generated at the canvas will be more pixelated.
Okay,
Yeah,
that is also true. Yeah.
that's exactly what I meant. Correct. Yeah. So it would be this one, but it will be pixelated thing
Yes,
as
yes.
to a geometric thing. Yeah. Okay. Okay, I got the thing. That's good.
So now we'll be moving on to the algorithm one. That is the safety checking algorithm, verification algorithm. So we had the problem of infinite search spaces. We'll try to reduce that to some finite number of to some finite space. So so that we can use some algorithm like DFS. So this is how we will do. For example, if I have a set of this initial region, this cube of initial region, and there are infinitely many points here.
Yeah, DFS is as in depth first search.
Yes, depth first. So these are like infinitely many points. So I am not sure what point should I start with. So and also there are like infinitely many points here. So what I'll do is that I'll like group them into these subcubes, so that you can think of it like a Rubik's cube. I mean, I'm dividing them into subcubes, and I am now uh, executing my DFS on this entire one region. So now there are like infinitely many search space elements in the search space. So this is the idea of some intuition for invariant region. So we'll be doing this using invariant region. Now, so this is the how is an invariant region defined.
I guess you meant finitely many. I thought I heard you say infinitely.
No, finitely many, sir.
Yeah.
These are like finitely many. Sorry if my pronunciation. So in invariant region, I do this by I group points such that image generated at that point is same as the image generated
one observation that I had was, I mean, go to the previous slide. The decomposition has to be kind of exhaustive, no? It has to
yes. It has to cover every point.
and I guess you will get to more details about how the decomposition is done.
Yeah.
To do it. So it has to be exhaustive. Yeah.
Yes. It should cover the entire space.
Yes.
Otherwise, there will be like spurious examples where it does not work, and I should implement some other stuff which and something like that. So now I'll be defining an invariant region. So an invariant region is like a collection of points. These contain some points such that image generated at that point given at 3D scene E is same. So for example, if 2 points are here, so the image generated by the camera of those points will be same. Same, I mean, in the pixelated picture, same number, the pixels which are colored here will be colored in the canvas of the other image, other pixel. So this is this, and then I won't be going into depth of invariant region right now because that's very complicated. I'll be doing this after some time, after I give you the algorithm, so that you can have some motivation to understand that. So here's my
one question. So this is it's not invariant over the
invariant in sense like
it's not, it's just invariant
in terms of
over
image
camera across
Yes,
time, or no? It is not. Is it
no,
across?
sir, not across time. At that point of, I mean, at dot point only, sir. Time is not related. It's not defined, yes.
No, but usually invariant means that
Yes,
if
sir.
I'm not sure. I mean, what does it mean to say invariant over camera image? That is,
I mean,
Oh,
can
huh?
can you go back to the invariant slide once? Invariant region. So
Yeah.
if I'm understanding
Yeah.
correctly,
I think I missed the detail here. Sorry. Yeah. So it's the one space invariant region around P. And P is
the point. So if I've been given a point here P, so invariant region around that will be set of all points such that the image seen at all those points will be same. So does this make sense? I mean, it's not
invariant in terms of space.
Yeah.
So
it's invariant over the space of points.
Okay. No matter what your positions are, those things will be the same. Yeah.
Yes. Yeah. Yes.
Yeah. Okay.
So because the canvas is highly pixelated, so this allows for this something like this. Now I'll be coming to the check safety algorithm. So first I'll be calculating the invariant decomposition D of R. So the invariant decomposition D of R is like I'll be dividing them into invariant regions. Given a C, I'll be given a region. Region means that cube, initial region and all. I'll be dividing that into a set of invariant regions, and then see the D consists of a tuple like this. IM is the image generated by all points in R1. So all these points inside this R1 generate the same image. So now this step is miscellaneous. I'm just using to do the for loop here. So now I'll do this compute trajectory of image Ri and Vi. That means I'll just propagate this set of points to the next set of points based on this autonomous vehicle model. That is, given this image, I'll feed that into the neural network of this vehicle. I get new set of points, and then these R2 is that new set of points. H is the convex hull of that, and U is irrelevant here. I mean, I shouldn't have written it here. It's the the output of the neural network. It's given here. So if H, the convex of hull of R2, intersects with E, which implies that given this region, after propagating my vehicle, I find that this entire set of points collide with some obstacle. If that's the case, then yes, it is unsafe. But if that's no, I'll check if so when I propagate, some points might reach the target region. Okay, so I won't be propagating them in the next iteration or in the next depth first search call. So what I'll do is that I'll remove that from this points, and I'll execute this again in check safety. I mean the remaining set of points in the region. So if I'll check that D is empty, this is just for a looping thing. If D is empty, I have seen all trajectories and I have iterated over all invariant regions. I'll return same. Otherwise, I'll go back and I'll get another this region from D and I'll do this again. Now, how are we decomposing this a region into multiple invariant regions? I mean set of points into multiple invariant regions. So the decomposition D of R is a set of tuples, like we saw in the previous slide, I am, R, where I am is the image generated by all points. So this is this. How is this done? So I am using the Z3. So to answer Shobit's question, I am not technically using Z3 to solve the entire problem. I am not formulating the entire thing using those constraints. I am solving parts of these problems using solver, not the entire problem. So this is so I'll take some point in R. I'll now check generate the point such that image generated at this point is same as image. I'll get all points such that image generated at all those points is same as image generated at P. So think of this as a black box for now, because this will be explained more in the rasterization process. That I am feeding.
Yeah, there is
this.
a question from Deep Pro. Oh, no, no, that's an old message. Sorry, ignore. Yeah, I think it's old message here.
So
sorry.
This is a high level view. I'll be using.
It's a new message, I think.
Hello.
Sorry, I think it's a new message. Deep Pro asked that by the negation of
a new message. Now I see. By
Yeah, so the question is by sorry, yeah, go on.
Yeah. Yeah, do you mean its complement that's outside of the region? Is that what, that's the question.
Sir, what's the question? Can you, I mean, I cannot see.
Is by negation of a region.
Oh, yeah. The complement, yeah. Yes. I just remove all those points which have been formed here. I mean, all P dash and P. I'll remove them from the region and then from the vertex set, and then I'll execute Z3. I mean, I'll solve this again. I mean, I'll do this again. So that way, I'll find most of the, all of the invariant regions.
Yeah, I had missed one thing in there. Okay, this invariance is, as you have defined,
yes,
has E in it, is it?
Huh? Yes, sir. That's the 3D scene.
That's the key thing, right? Yeah.
Yes. Yeah. Consists of VT and then.
That's why you're getting. Okay. So with respect to E, yeah, that's.
Yes.
Okay.
Because I mean, I can assume that E is fixed and then do this, but in the paper they do this. So now I'll be. So how are we checking for collisions? Since, for example, if my initial region is defined as a polyhedron of this kind of as a cube, so when we are assuming that all the translation thing, the translation by translation I mean that when I translate all the points in the this initial region to the next intermediate region, the translation is linear. So the convex hull is preserved, which implies that if 2 points are in my this convex region, will be the same 2 points in this convex region. So this is why I can check whether it collides with any any triangles in the C by calculating the convex region and checking if that intersects with that convex hull or not. So now this is for computing trajectories. So like I showed in the computing trajectories thing, this is the same formula. So There's nothing
Yeah, but
new
here I
here.
have a question. So
Yes,
the
sir. Yes.
region is
Sir, where?
is like a set of points, is it? I mean,
Yeah. Set of
you're
points.
showing it already as a like a polyhedra, which is
Yes.
kind of a convex hull. But what you're
Yes,
saying
yes.
is region is just a space, okay, and then you come
Yes, yes.
a convex hull, which could
Yes,
be
yes.
kind of an over approximation, right?
Yes, sir. Oh, no, not an
No,
over
no.
approximation. That's
Ah.
the point, because the
Ah,
translations are linear. So
yeah.
2 points here will be the 2 points there they'll be near. For example, if this is not linear, it could happen that those points could go like, so this point could go here and this could go there, and then there will be something like an over approximation. But in this case, since I'm assuming there are infinitely many points, and this invariant, this is an invariant region, sir. Okay, this is not the initial region, so the all the points should be close to each other. That's why convex cell works here.
No. So,
Yeah.
firstly, one question that I have is, how are you keeping track of invariant regions in memory? Are you
Yeah.
keeping? You can't do it as a set because it will have an infinite
That's right. That's right. That was
I-
the question that I was leading to. How exactly is the region represented in the
I can
first place anyway?
write them as a equation of planes.
So it's a polytope.
Probably, I can do this. For example, it's not given in the paper, but I think that I can just calculate the convex hull of this entire thing, these points, the H, sorry. So these H points, and then I know that any convex combination of these all points will give me the convex hull of this. Then I can just store the boundary points of that.
Sure. But what do they do in the paper?
They don't do anything, sir. They just say that there is this region and all. They don't
No, but
specify.
they must be keeping track of it somehow as a.
Yeah, they are forming equations. Like they said that
What kind of equations are they?
uh, uh, I mean the equation of plane. I think that this is. I mean they don't explicitly specify what kind of equations, but they say I think it should be like given this region will be defined by a set of points such that all the points inside this convex hull are inside this plane, then inside this plane, inside this plane, inside this plane, and inside this plane properly.
Okay. So the region is indeed a polytope, right?
Yes, yes.
And they are keeping track of the equations of the planes that form the sides of the polytope. Is it?
Yes. They haven't given out the actual details.
Yeah,
I'm
but if
sorry for
it's
that.
already a polytope, then why do
Yes.
you need to compute the convex hull again?
Yeah. So what is the convex hull that is being computed here?
This new one, sir. The convex hull of both these points, sir. Something like this. It's being computed.
No. So okay. So firstly, the vehicle dynamics is linear. So
Yes.
what does that mean? That means that in the next time step, wherever a point will go, it is only a linear function of where it was. Is that
Yes.
what that
Yes.
means?
Yes.
Oh, so then if it was in R and now it is in M, then this whole region R is being shifted linearly to R prime, right?
Yes. That's why this.
That is just some variable transformation when you talk in terms of the equations of the plane. So why do we need a convex hull?
Uh, I mean, we are calculating this convex hull. Actually, you are right. You might be right because I just need these points. So I do not need to calculate if depending on how I am storing these all and how I'll be recalculating convex cell, I might not need this convex cell. I'm assuming I have this convex cell. There's no calculation given.
Oh, so they're not using any convex hull libraries or anything like that for
The
this.
PPL libraries, they're maintaining a PPL library. That's the
Right. So
implementation
then,
detail.
Yeah, maybe since they're decomposing that original region into these invariant regions, maybe for the invariant region computation, they need the convex hull in order to
Yeah.
represent them.
no, but yeah, but that detail you haven't given yet, right? So we're just assuming somehow we have invent regions right now, right?
Yeah.
So
I mean, those I'll discuss in the implementation part. Right now, I'm
Ah.
just expecting that there is this convex cell and then.
Used to check the region for also. Okay.
Technically, they are using a library called PPL polyhedron something like I don't remember the full form, but PPL libraries to maintain constraints regarding this polyhedra and to find the convex hull of those regions, and then also finding the invariant regions. It's using that library. And I'm not sure how the internals of that library works because I haven't implemented it yet. So now moving forward, so this is the computing trajectories thing.
No, it's not still clear to me. How is the collision checking actually happening?
For example, if there is some edge here, which is inside this, which goes inside this convex hull, this entire
Which
thing,
convection?
this R and R dash.
Wait, but
Yeah,
R and R
sorry.
dash are two different polytopes, right?
Yeah. So I'll be constructing this entire this. I'll be in the paper and the algorithm. It does this only in this compute trajectory thing. This thing, convex hull of R dash and R.
Why?
Oh, so they're taking a convection of
Oh,
R dash and R.
convex of R and
So
R
Yeah.
dash.
So that is what you should. That's why I was sort of getting. Yeah.
I mean, this thing,
Okay,
sir.
but that
This
means if
entire
they're
thing.
computing the convex hull of R and R dash, then the checking is not very accurate, no?
It is probably, sir, because
Yeah.
when I'm moving my vehicle from here to here, I'm assuming that it's moving this. So if there's
Okay. So basically, the convexel of R and R dash covers all possible linear paths that start in R and end in R dash.
yes.
So if there is an intersection with the convexel, there has to be some path that intersects
Yes. Yeah.
the triangle as well.
Yeah.
Also, this is linear, so
But the reverse is not true, isn't it?
The reverse is this the reverse
Isn't
true?
it,
sir, what is
Lucky?
the reverse? Sir, what
The
reverse?
reverse means, if there is no collision with the convex hull with the triangle, yes, it is safe. Okay.
Yeah,
But,
I mean, yeah.
But the convex, if the reverse, that is, they could be just because if it says there's no.
Oh, so you mean
there
that
is collision, then
okay.
it may have some extra spaces, the hull.
Oh, yeah, I get it. Like you mean some spurious thing.
Yes.
Yeah, so
So
if there is a collision, so if there is a triangle which intersects the convexel, does it always mean that there will be an actual point in R and R prime and a path between them so that the vehicle
yeah.
if it
So since this is linear, any point, if I this point and this point, suppose I don't look at these as polytopes, look at these as points. So if I have this point here, I have this point here, I'm just moving this from this to here. So the trajectory of that point, the path will be this only, right? This thing
it
and
will just
any
be some
edge.
line connecting the
Yeah.
point in R and R prime.
Yes. So every point here is mapped to some point here. And this forms the entire this. That's why the convex hull is maintained. And if I add an
this
edge,
convexel basically exactly captures all the possible paths between R and R prime.
yes, sir.
So it's
Because for
precise.
the
There's no over approximation going on.
yeah.
Is this guaranteed because the kind of trajectories that you're also looking at are kind of linear trajectories?
Yeah.
As some kind of, like a pipe-like thing, okay?
Yeah.
Or a pipe with a polyhedral pipe kind of a thing.
Right.
Yes.
So if my car were to sort of take a turn between R and R prime, like take some smooth arc-like turn, then the convex hull will not work.
Yes. Because then there will be like, for example, if there are just 2 points here, and I am doing a non-linear transformation, one can go up here, one can go down here, and then if I calculate the convex hull of that will be like the over approximation. It will include many more points and all.
Yeah. Okay.
So this is this, and then this is the computing trajectories thing, the same one I showed in the at the start. So this is the compute trajectory algorithm. So what I'm doing is now this Fn, I'll be describing it now, is the output of the neural network given this IM, given this image. Okay. And this neural network is a convoluted neural network. This neural network outputs a L into 1 matrix. So I need to convert that to a 3 into 1 matrix. For that, I use this M.
Just a second. So by convoluted neural network, you mean a convolutional one, right?
Yeah. Sorry. Yeah.
Sure. Okay.
and then R dash is like these next set of invariant region. So R dash is this, all the positions here. And now I'll calculate the convex cell of R dash and R, and then I'll return that to this U R dash H as that tuple in the algorithm. So this is how it computes the trajectories. Now, the drawbacks of this is, for example, there are possibly exponential invariant regions. For example, if I have like n points here, I mean, if I am considering, if I'm grouping points like 1 cube, 1 cube, 1 cube, 1 cube and all, there it can have options to go to max. For example, if in any convex cell, there are like d maximum invariant regions possible. So I can say that given this point, it has like d to the power n to the power d possible partitions of this. I mean, I can make d to the power n partitions of this. So this is why this is exponential. Also, time complexity because of this only becomes exponential. One drawback these are all, I mean, I made this up, so might be wrong. So the one algorithm, one drawback of this algorithm can be that it does not merge invariant regions. Suppose I have one invariant region here, R1, and I have another invariant region here, R2. After one iteration of the algorithm, it projects, I mean, it propagates every point in R1 to here and every point in R2 to here. And now we have this these points in a similar region, but since they are in different branches of the DFS tree, I cannot like use only single computation to calculate all this. So this is my one drawback I can think of. So now proof of correctness. So the proof of correctness uses this. I'll be first proving that this algorithm terminates.
No.
But
One question that I had in the previous thing is, you say that there are infinite invariant regions. When you decompose,
no, sir. Invariant regions are finite, sir.
Yeah, but then what do you mean possibly exponential invariant regions?
For example, I mean, I am assuming, let's assume, I mean, I'm just assuming that a unit cube in this set of points have the same invariant regions. I mean, they correspond to one single invariant region. And then D is the maximum number of invariant region I can have here. I am not calculating that. I'm just saying that D is the maximum number of invariant region because I know that it's finite. Therefore, there must be some maximum number of infinite D. Okay. So now my algorithm has like n to the power D for each point here, for each invariant region here.
Each decomposition has finite region, but they can be
Sir,
infinite number of decompositions. What is infinite here?
sir, where infinite?
Oh, I mean exponential. I'm sorry. I'm using the wrong word. Exponential in what? I mean, when you do the decomposition, they could be exponential. Although they're finite, they can be exponential. Okay,
because
sorry.
There could be like multiple, I mean, partitions of that. I mean,
okay.
So
That I
I
understand. Okay, sorry. I got confused.
Why is it that there will be exponentially many such regions?
Sir, so I am assuming that one unit cube here corresponds to one invariant region. Okay, so now the maximum number of invariant region decomposition I can have is like it's something called D. So now every point I have like a D options I can put into. So I can have like a n to the power D, something like that. It's
Wait,
just
I don't understand. So, what are the points that you're putting into D?
one cube, sir, one unit cube.
What is D?
D is the maximum. I mean, I'm not putting them in D. D is the maximum number of invariant region in my this thing in any such invariant region.
So D is the maximum number of
decomposition.
invariant regions in your whole
Maximum
3D
number
space?
of yes, sir. Yes. because it is technically finite, right? So I can bound it
Right.
with some number,
Right. So,
and then
sure. And what you're trying to show is that this D is an exponential in what?
I mean, I am trying to show that the number of invariant regions, I mean, the number of, the number of decompositions can be exponential. That's why,
The number of decompositions, as in.
yeah, because I can put this one unit cube into one decomposition. I have like the
No, sorry. So
options for that, right?
when you say decomposition, I mean when you're splitting up the region into these cubes, isn't that the decomposition that you're talking about? Like
Uh,
you,
I mean, I'm
decomposition
dividing
is
them
just a
into,
part.
yeah,
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 yeah, as if I understand you correctly,
yes, yes,
what you're
yes.
calling a decomposition is just a partitioning of the whole space
Yeah, yeah,
into
yeah. Yes, yes, yes,
infinite
yes,
regions, right?
yes, 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 yes. So
Okay.
I'm
And
yes.
in this
So
case, what you're saying is that these cubes are your infinite region. So these cubes are your decomposition, right?
yes, but now I am like merging them together. I mean, technically I have to merge them, right?
Why?
If I may interject here, is it because that the decomposition is fine, but as you move in the next thing, that there could be some kind of a branching in the different decompositions that are possible, and therefore every time that you move, there will be some branching that is adding to your exponential possibilities of possible thing. Is that?
Yeah, yes, sir. Technically, it's that only because
Uh,
I am like making it more complicated, but it's the underlying principle is this only because there are branchings, and then I
No, but
for
there is no branching, right? I mean, that is the point of the invent region, right? Since the image is the same,
I mean,
there
branching
is.
in this sense, sir. For example, this cube, I am dividing them into multiple invariant regions.
But why are we
Okay.
dividing the cube? So what is the cube? I thought
So
the cube was the invent region.
yeah, but in the next interval, I am doing this right. Given suppose this is my I. Suppose this is my I am
Okay,
decomposing
sure,
that into multiple invariant regions. Okay.
sure, yeah.
So I am assuming that capital D is the
It's the
maximum
number
number
of
of,
inches.
yes, yes.
Yeah.
And then I am assuming that one point here, I mean, one point, I mean, there are infinitely many points. So I am assuming that one single unit cube corresponds to one invariant region. And then I am putting those two, this,
I
and
don't
the,
understand. Sorry. I followed you when you said that there are capital D many invariant regions in your initial region I. Uh, and then what you're saying?
and then I'm saying that I have like cubes here. Hello.
So what are these cubes?
These cubes, I mean, I'm saying that this one cube corresponds to one invariant region. That means that any image I produce in that cube is same.
Okay, so sure. So there's some tiny cubes in this
Yes, sir.
I.
Oh, sir,
Each
how
of
do I?
this is an invent region, and then what are we doing?
So I have like D. D is my maximum number
Yeah,
of.
this will be very helpful. Yeah,
So I have this cube.
Hmm.
just draw 2D things. It's okay. I mean, I
Okay.
think yeah.
So technically, I'm assuming that this single thing is my invariant region. These points are my invariant regions. Okay.
These small cubes are invent
Yes.
regions,
Yes. Yes.
and they're capital D many such things.
Yeah.
Yeah,
Yeah.
sure.
Uh,
Then
I mean, I'm assuming that there are like not capital D. So I am saying that the uh, number of such a decomposition. I mean, let's say D. Uh, let's say D is the maximum such a decomposition of the invariant region. So D can look like this, right? I mean, in my algorithm, this thing can something like this could be D. I mean, the maximum number of this. It necessarily should not be this. Every single point can be, but yeah. So, and then, are you following?
no.
Can I send this to you after this?
Yeah, maybe that's a good idea. Let's just move on right now. Yeah.
Yes. Yes. So, sir, how do I solve this annotation?
Yeah, the way I'm looking at it is, I think there will be some questions, okay, that if it's not answered, in all the presentations there are some. And there is I'm actually thinking as we go along that indeed that needs to be noted down and that need to be clarified later on. But once
Yeah,
again,
yeah, I've been keeping notes generally.
yeah, that is one thing. And yeah, I mean, I think maybe I don't know if this comment of mine will help or not, but there is no branching when you given a particular decomposition of the region. When you move to the next trajectory, you have to decompose again, correct?
Yes,
No,
yes.
you don't, right?
Uh,
That's why I was a bit confused, right? I
you
mean,
don't need to decompose again.
if I understand correctly right now, I mean, we will have to decompose the initial region, but
Yeah,
then each of the invariant regions in that decomposition, when we move it forward, we don't
yes.
need to compute any more decompositions of that, right?
Oh, sir,
So,
we do, I think, because, sir, wait, sir, I'll just confirm. Wait, uh, wait,
Yeah,
can you go to this
yeah, yeah.
flowchart of the algorithm that you had?
I mean, how can I erase this?
I don't know. I don't know what you're using to. Oh, is this the one
Uh,
inside Zoom?
yes, yes. Oh, I did
I
it. I did
see.
it.
Ah, okay. Okay. Yeah.
So, calculate. I call check safety, and then this calculates the invariant decomposition T of R again.
Yeah, but no, see, the loop is going back to the one after the calculating decomposition TFR, right?
Yeah, yeah, yeah. But sir, this thing. Check safety again. It's calling it again.
Right. But see, I don't understand why that should be needed. Because,
Yes,
um, I mean, see, we have R. So, what are we calling check section? Some R2 minus T. R2 is already an invariant region. So, R2 with T removed will also be invariant, right?
yes, yes,
So the decomposition of R2 minus T should just be R2 minus T itself. There should exactly be one invariant region there, no?
yes, yes.
So there should not be any further decomposition that needs to be done, right?
Oh, so the thing is, I had this R1. I did this, sir. I propagated this thing. Oh yeah, you might be right. Uh, uh,
So does the paper mention
yeah.
or argue about the exponential
no, it is
number of
not, sir.
regions somewhere?
It is not.
Okay.
Right,
I
right,
was
right.
just
In
trying to
that
giving the
case,
intuition, sir.
yeah.
Yeah, 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 yeah. Yeah.
So the decomposition is maintained, is what both of you are agreeing on, correct? So then there
Yeah,
is no R1
I
to
think
R2 transformation, huh?
no, there is an R1 to R2 transformation definitely because R2 is basically whatever happens in the next time frame.
Yeah, yeah, yeah. Also,
But
sir, can okay, sir. Sorry.
no, no, go on, go on.
No, no, sir, I meant that, for example, if this needs to be done again, because suppose I have this cube here, I am now linearly transforming it to this. Can I? But is it necessary that this will still be the invariant region? Because
Ah, okay, 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 okay. No, no, you're right. You're right. You're right. You're right. You're
so
right.
this is the point. So I'll
You-
have to then decompose it
yeah, there
again.
may not be. It may not be invariant. Yeah, 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 yeah. Okay, okay. Yeah, yeah,
So
yeah.
it
So
means then you might have to add new invariant regions.
yes, sir, yes, sir. That's why
Yeah, and that
there
might be
is branching.
exponential. Okay, okay,
Yes,
okay.
yes, yes.
Yes, yes,
So
absolutely, absolutely. Good, good, good.
so
Yeah, I think I was.
that's why I was saying this. So
Yeah,
I was like doing this maximum D, and then I was trying to put them in these. I was trying to form partitions of this, and there are like maximum D, so there will be like maximum D partitions at something like that.
So each time that you move, there can be more. You can add more regions. Is that what?
Yes, sir. Yes, sir. Yes, sir.
That is possible. Therefore, then that could multiply. Huh? So,
Yeah. So the thing is, I think I should. It's okay, sir. Sorry. I'm
yeah.
sorry, sir.
no, 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 no. This makes
Yeah.
sense. This makes sense. Yeah, I think somehow this point was not coming through, but I think what you're saying is correct. Yeah.
Okay, sir. Then I'll be.
But it's still worth confirming if they have not addressed, even if this is true, okay, which seems
Yeah,
like
yeah,
the way that you said this thing, then the algorithm, the exponentiality and the scalability of the algorithm somehow has to be addressed, whether they have mentioned in the paper or not. That's worth checking as a post thing. Okay, go ahead. Yeah.
yeah.
Now,
So they haven't
so in
mentioned. I
terms
was
of
just.
time, I'm saying I'm going
Yes.
to give you it's 11. So you have Regulation time is still 11:30 because you started
Oh,
only 10 o'clock. But I'll
okay,
give
sir.
you another 10 minutes because we do not have all the people, okay, that are
Yes,
there.
sir.
So, yeah. So another
Uh,
15
s-
minutes we can
s-
take. Yeah, please go ahead.
so now the proof of termination of this algorithm, I'll be using the contrapositive of Koenig's lemma, which states that if the Koenig's lemma states that a tree that is finitely branching but infinite must have a infinite branch. See, the contrapositive of that will be that if a tree has a finite branch, then it must be finite, something like that. So I am associating a positive real number dr. Should I prove this? I mean, should I say this? It will waste some time.
I think you can skip the proof
Yeah, I
maybe,
think
or
so. I agree.
So and then proof of correctness is like very trivial. I'll be assuming that till this.
But instead of the proof, what is
yeah,
your
intuitively, why do we need, what is the,
intuitively?
So yes, yes, sir.
Yeah, why should it terminate? Because there intuitively, what is the factor that is reducing something usually in
Yes,
termination?
sir. I'll be arguing that the DFS tree which is formed is finite.
why
What
is
is
that
finite?
I mean, why is that finite? I mean,
I'll be using Koenig's lemma for that. That
What is finite? Did you say? I missed it.
sorry, sorry. For example, we are like executing a DFS algorithm, right? We
Yes.
are taking an invariant region. We are then converting that to multiple invariant regions, and then we are iterating over that. So this is branching, like you said, sir. The branching thing. So that is like a DFS tree. Hello,
Yeah,
hello,
yeah.
sir.
But the termination condition, what you have in there
Yes,
is
sir.
that you have the D has to be empty. You have to look at every invariant region in
yes,
the
yes, yes.
that is increasing after every step in the trajectory, and then eventually even the depth first thing will have to
Uh,
somehow, yeah.
so I'll argue that I'll attach a distance metric r dash to
Uh,
each this thing. I mean to each invariant region, and by progressive assumption, I'm assuming that my this thing, my points, my invariant regions are moving forward. Okay.
right. So can you explain the progressive assumption a bit? I think that will clarify intuitively, because I think the termination simply comes from the assumption.
Yes, 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 yes. So progressive assumption means like my this invariant region, any invariant, any set of points I have, any trajectory, any point should move forward in z direction at each step. So
And the final region T is always at the end of the Z
yes, yes,
direction.
yes, yes. So that's the like high level view of this. So
okay.
I have a reference for this. It's the Suleiman's ball game,
If
sir.
D of R prime is less than D of R, you mean the number of invariant
Then
regions?
no, sir. The
Oh,
d
the
means distance.
smaller.
Distance.
It is smaller.
The
No, no, no.
distance is the distance, sir. The distance.
Distance. Oh, my.
Yes. Sir, I am associating a real number to dr for a region r which equals to the maximum distance from any point in r to any point in t. So the
Hmm.
maximum distance. So that is reducing at each step. I am saying that. And then
Yeah, either you have to
yes, yes, yes.
find a check for, violation of safety or not. Okay, that's
Yes, yes. Also, I argue that if this D is different here, unlike the previous thing, which I was using D for something else. So D is the maximum distance between my vertex, my starting position, my initial region, and my target region. Okay. At each step, I am saying that it's reducing by. I mean, I am moving forward by at least C. So the total, I mean, the total number of nodes in one branch of the DFS tree will be like D by C. Is this clear?
yeah. I think we have to, we have to trust you. Okay, and there might be some discussion that we can have. Okay, so given that I'm giving you half, uh,
And
half an hour. You have half an hour in regulation. Okay, another
yeah,
15 minutes. So, yeah, please go ahead. So you have to present two more algorithms, and that would be the end. I mean, yeah.
then I have the results.
Um,
Results.
results. Okay, yeah.
So proof of connectedness, I am ignoring for now because it's simple. Now, this is also there. How is invariant region generated? I'll just walk through that. So now we know the significance of invariant regions and how they make the enumeration of trajectories possible. So now we'll try to figure out how it's done. So we'll now first understand how our image is generated. Something like this happens. For example, if this is a triangle in the scene, I project that onto the canvas, and these are the two pixels, not pixels, the positions corresponding to these triangles in the canvas, on the canvas. So I'll be moving fast. So this is a viewing first up. This is the range of uh, this is the, like, for example, in the case of our eye, there is this blind spot where we cannot see. So this is something like that. Anything which is here, any triangle which is inside this viewing frustum, this pyramid shape like 3D object, that will be visible by this camera. And now there's something called perspective division. So any point here, consider a point here, I'll be projecting that onto this canvas here, right? So I'll be using the similarity of triangles equation to form this. Suppose this is at camera is at position 0, 0, 0, then L divided by this Z dash dZ naught equals to this Y divided by this Y naught, and then I'll be able to calculate this Y naught dash position. I'll just do this. So similarly for X, similarly doing this for X and Y, I'll get these points, assuming the camera position is 0, 0, 0. And now, so when my camera position is not 0, 0, 0, I'll have to do something like this. I'll have to, for example, if my camera position is somewhere here and this is here, so the distance between this and this should be x naught minus xp, this distance. And then I'll use the same similarity of triangles thing to get the equations for the projected pixels, for the projected points in the canvas. Yes, so PW is the width of this. Also, then I'll be converting this to a pixel. For example, this entire thing gives me a 2D coordinate. This thing gives me a 2D coordinate of this point on the canvas here. And now when I divide it by PW, which is the width of 1 pixel in meters, this is the width of 1 pixel in meters, I get the corresponding pixel here. Does this make sense? Hello? Hello?
This conversion kind of, I can trust you, but you said that, how are you decomposing into invariant regions? I thought that.
Yeah, that's coming, sir, that's coming. I mean,
okay. Yeah, okay.
So the motivation for this is like, and this is like bonus, I'll ignore this. Now, what's the takeaway from all this is that multiple points in the 3D scene map to the same pixel in the canvas. So now the invariant part is getting together. So I'll be using something called a pixel torch to form this invariant region. So what is a pixel torch? Given AB, given this point here, and camera position P, a pixel torch is like a frustum, this torch beam shape. So if I move this V naught anywhere here, the pixel that will be activated in the canvas of this camera will be this only, right? So if I move V naught somewhere around here, this, so the activated pixel will be this only. So this is the idea of pixel torch. Am I going too fast?
No, that's fine. Yeah.
So here's this. So how will I be? So for example, this is my. Now I'll demonstrate how I'll be using pixel torch to generate invariant regions. So suppose I have a P here, I have a P dash here. Suppose this.
So just to understand, so any point inside the pixel torch will map to the same pixel on the canvas, right?
Yes, sir. Yes, sir.
Okay.
Given a camera position. So suppose I have been given two camera position. One is P and another is P dash. And for example, just take this case. Yeah. Now, in terms of P, if I move my V naught here anywhere here, this should activate this pixel only. And with respect to P dash, if I move my point anywhere here in this red part, the projected pixel will be this only, right? So now, if I move this pixel in the intersection region of this both of the torch beams of these both, then I can say that if we not move in a position such like this, then this pixel, I mean the top right pixel will be activated in both of them, right?
In the overlap region.
Yes, the overlap region. So if I move my point here, so similarly for this only, sir, this also for V1 also. If I move this thing in the intersecting pixel, the intersecting beams of my pixel torches, the projected projected point on the projected pixel on the canvas will be same for both of them, right? And similarly for this V2 also. So this is how I'll get this. So I got a P. I'm assuming that there is only one triangle in the scene right now. Okay. So for this P and P dash, I can see like two images. I mean the images generated at both canvas are same, right?
Yeah, but they can't. Yeah, but they can't get split here. Or why can't they get split?
Sir, what do you mean by split?
So if in that green thing, that region is, I mean, an invariant region, huh? Red one, the corresponding one, I'm saying.
Oh no, sir, this is pixel torch. So if I move my pixel anywhere in this blue area, V0, I can move anywhere here with respect to P. The projected pixel will be this only.
So what is the new set of so are you trying to see how you're decomposing with respect to 1P, or you're trying to explain how, given a set of decomposition, you will go from P to P prime? What are you trying to explain?
I'm trying to explain that for 2 points, the image generated will be same, something like that. So if I move my pixel here in this part of my.
So if I recall correctly, invariant region is basically a set where if I pick a P and a P prime, the image generated should be the same, right?
Yes.
But then it is obvious, no?
Yeah, it is obvious, but I am just trying to formally do this.
So,
The intuition
but that set can somehow be represented, as you said, using a conjunction of linear equations. So those equations are basically, you're trying to somehow intuitively tell us how those equations will come.
Yes, sir.
Yeah, okay. That's fine. Yeah.
I mean, this is interesting. So that's why, I mean, you don't have to. Should I? So, I mean, so this
go
is.
ahead. I mean, so go back and explain as you were.
I think you should. Yeah. I mean, you have time.
Yeah.
You can go ahead. You should. Yeah.
Yeah. I think the invariant region is important. I mean, in my mind, at least, it's as important as algorithm one, and perhaps slightly more than.
Because it's like some result of
The
this
crux
paper.
of the I mean, if you can't do the invariant decomposition, then you can't do any of the things you're doing in algorithm one or
so
2 and 3 for that.
Yes.
Yeah. So can you go back and show once? So basically we have P and P prime, and if what we're saying is if we slightly shift things, then all the vertices will fall inside the pixel torch of both P and P prime. So the images will be the same.
Yes. In the same pixels. That's the thing. So I have tried to visualize it.
Yeah.
Now, so how will I be able to calculate this invariant region using that information? So that's my main thing right now. So
yeah.
So while doing this, I can get a constraint for this thing, right? P dash. I mean, I can move it here, such that it should intersect with this point.
Okay, so the constraint for P dash would be that you calculate out what the equation of the this pixel torch for P dash is, and then the constraint should say that inside that pixel torch, V0, V1, and V2 should lie.
Yes. So
okay.
Intuitively, I'll be so this is the intuitive thing. I'll be calculating my this thing, my invariant region corresponding to a ZP plane, that is a plane parallel to the XY plane. So this is, suppose this is the XY plane. So I'll be calculating this this pink set of points is the invariant region, corresponding to the ZP plane. That is, if I move my camera here, the projected pixels will be same. So I will come to how. So by doing this, what I'm doing is like I am just making a invariant region in the ZP plane only. And now if I move this plane a little bit ahead and I do this similar process again, I'll get another set of a smaller frustum like a shape of this invariant points. Where when I move this, the positions of these triangles does not change. So when I do the convex hull of that, this I'm not sure, is then it will result in one invariant region. So something like this happens. So I have the intersection photo in my following slides that will make stuff clear. But this is like the graphical view of whatever we are trying to do. Now, assume that there is only one. I had a lot of derivations here, but I removed that because considering the time and all. Now, suppose, so this is my projection formula, which I showed in one of the previous slides, right? So the A naught is the x coordinate of the projected pixel for any A. And B naught is this. A naught, B naught, A1, B1, A2, B2 are the projections of V naught, V1, V2 respectively on the canvas. And these are given by formulas which we discussed earlier. And we are given a scene E with one triangle only, that is V naught, V1, V2. So now I know that this A naught is greater than equals to this thing, and this thing is less than yes. Yeah. And this thing is less than equals to A naught plus 1. Right? A naught is less than equals to this thing. If I remove the floor function, and then that thing is less than equals to A naught plus 1. So I do that for all of these, and then I find bounds for these. Hello?
Yeah. So you're basically trying to get a representation for the thing when you move from one position.
Yes.
And these are some linear transformations that you're.
Yes.
Okay.
Yeah, so those will give me some kind of constraints.
V naught vertex is in the same pixel. And for similarly, if I do this for the V naught, V1 vertex, I'll get this thing. And now I'll do this for V2, I get this thing. So doing all this, I get one. So if I move my camera here, the V naught will be projected onto the same pixel. Okay. If I move my camera in the ZP plane here, my V1 will be projected onto the same pixel. And if I move my camera in this region, my V3 will be projected onto the same pixel. So now if I move my camera such that all three of these are constrained, I mean, all three of these are maintained. That is by taking the intersection of all these planes, which I can move, I get something like an invariant region. So this is the motivation for the invariant region. So.
Okay, you have to move.
Yes.
Yeah.
So I'll not be discussing this, but I'd like to say that the paper formulates all these steps, the process of rasterization, that is converting 3D scene to image, and the and this process also into logical sentences, and it then feeds that to Z3 to solve those constraints and generate images. So it's using Z3 to generate images and do all those steps. So now we are coming to the abstraction-based algorithm. So, the idea is that there are we have been successful in reducing the size of this the initial region space, but now I'd like to also decrease that size too. So I'll be grouping invariant regions in this algorithm. So now, so the one problem it might have is that it might over approximate. I'll be coming to this soon, and then the proof of correctness and termination, I won't be discussing that because those are like similar to the previous one, and which I did not discuss fully. So now, suppose these were my invariant regions, right? Given a cube, suppose these small cubes were my invariant regions. Hello?
Yeah, we're here. Please go ahead.
So suppose in my given this, I first group them into invariant regions, right? I group the points into invariant subcubes, and now I'll be grouping these invariant regions into uh, groups of invariant regions. For example, I group these invariant regions into one single group. I group these invariant regions into one single cube, and now I group these into one single cube. Also, to be noted is that these shouldn't be, I mean, it's not necessary that they should be in a same place, because we'll be grouping uh, this based on our I'll tell you. So,
Yeah, but what
based
does
on,
it mean to group?
uh,
You're not merging them or computing convex hull or anything.
yes, sir.
Yes. Huh?
So in algorithm one, we group together images, group together points based on the image generated at those points, right? So,
Yeah.
so in
What
this,
does it mean? Yeah, here you're merging? No.
we are grouping invariant regions here, technically merging points, technically merging invariant regions only.
Yeah, but then if you merge them, they may not be, no longer be.
So
Okay.
so it will over approximate, but I'll be merging them based on the
Okay.
output of the neural network. So
Okay.
neural networks, I feed the image, and suppose it tells me to go left. I mean, by some degree left. Now, all the I mean invariant regions which have that similar control output of the neural network, I'll be grouping all of those invariant regions together.
So they are sound, these grouping and merging is sound with respect to the linear trajectory that you take. Huh?
No, sir, this will over approximate, I think.
No, over
This,
approximate, yes, but it's a sound over approximation is what I'm saying. It
yes,
won't
yes, sir.
lose any information. Okay.
No, sir, no, sir. No, sir.
Yeah.
Because technically we are just grouping together points. So we'll be representing, I mean, it's exhaustive, as you said. It will be exhaustive.
But when you group them,
Yes, sir.
it'll still be invariants. Yeah, there'll be the invariant regions.
No, then they
No,
won't be invariant regions.
They won't
Yes.
be. Okay.
Yes, yes.
So they can be then false alarms. Yeah. Okay.
Yes, yes. So my algorithm here works something like this. Suppose I am given this invariant region, initial invariant region I. No, not invariant. Sorry. Initial region. Sorry. This is the initial region I. I do the decomposition on that. Then I get these two, R1 and R2, in the same invariant region. I mean, I get these four invariant regions. Okay, these four invariant regions. Now, by grouping thing, I'm checking those. I check the control in output of these invariant regions on my neural network, and I see that the control input which is generated for this is similar to this. So I group them together. Okay, so I group these blue ones together. I group these white ones together. And now, so this is the convex hull that is generated, this thing. So now in the next step, I generate the convex hull of all this thing of R1 and R2, and I execute my algorithm on that. Is this all right? Hello?
You're going to execute on the convex hull of R1 and R2?
Hello?
Hello.
Can you say it again?
Sorry, which algorithm are you going to execute on convex hull of R1 and R2? You're coming to describing that, is it?
Which algorithm?
So you said that you'll take the convex hull of R1 and R2 and you'll execute your algorithm.
Yeah, this only, sir. I'll be recursively
Yeah,
calling
yeah,
this
okay,
algorithm.
okay.
Oh,
Sure.
sorry. I did not hear. I'm very sorry. So now I have this region. Okay. I call this uh, this H1. I call this H1, the convex hull of that. I call this
That's
algorithm
the
to
blue boundary,
say
the one
this
with the
one.
blue boundary, is it?
Yes, sir, the one with the blue boundary, and this one with the pink boundary is the convex hull of these 2 points. This group, white group, and this is blue group. So now I'll be doing this. Uh, I'll be executing the algorithm again, and then it will group these points. It will group this, and it will group this. Okay. It will, the red part, it will say that these are in. So the wait, I'll explain this properly again. So after I get this, I divide this into 1, 2, 3, 4, 5. 5 invariant regions. Okay. Hello,
Yeah.
What are you dividing into 5 invariant regions?
sir. So I get this thing, the blue box, the blue polygon. And now I am executing the decomposition algorithm on it. I'm decomposing this into multiple invariant regions. Okay.
So when you say execute the algorithm on it, what do you mean? Which algorithm are you executing on it?
Algorithm 2, sir, the check abstract safety.
And so what does the algorithm do? I mean, I can't seem to understand this if you don't tell me what the algorithm will do, right?
Yes, sir.
So yeah, I think go on.
So
Sorry, I think there's too much interruptions right now. Let's just go on.
hello.
Yeah, this is the flow chart of the new algorithm too. Huh?
Yes.
Yeah, okay.
So I'll first calculate the invariant decomposition D of R given R. I'll group them into regions. I'll then use this stack. So I am using this stack because I am technically doing the DFS thing in this one. So that's why I'm iteratively executing the DFS. I'm not calling this again, this abstract check safety. So now I'll push GI to GI, every this group into my into my stack. And now I'll pop one G1 from my stack. This thing is not needed. So ignore this. Now I'll go to R1 and I'll calculate the convex hull of G. G1. And then I'll do this, let IM Ri belongs to G. And then I'll compute the trajectory of that. So technically this is, so that's why I had this, sorry. So what I'm doing is that I'm grouping the invariant decomposition into groups, and then I'm calculating the convex hull of that.
Okay. So there was
It should be
when you
G1.
were saying apply an algorithm, we're talking about compute trajectory.
Not yet.
Okay, sure. Sorry, go ahead.
I mean, it is done behind the scenes.
Yeah, okay, sure.
For example, when you're right. Sorry, I'm very sorry. So when I get this, I execute the compute trajectory thing. I propagate this entire thing into a new area, and now I apply the convex hull and all those there. So this is the abstraction of that. Now, I propagate the entire group. So the point is, I am propagating the entire group here. So let IM belongs to G. I am taking one image, and I am computing trajectory based on that image on this entire R1. This R1 is this G1. I'm sorry, I forgot to write here G1. Does this make sense till now? Hello.
Somewhat.
This one, I'm very sorry. This should be G1.
Which should be G1? We can't see it.
Sir, this one,
okay,
this convex hull G1. Yeah, because
that is okay. Yeah.
Okay. That's why I think it might be
Of
confusing.
G1, but G you're maintaining. So for G1, you're computing that thing.
Yes.
But you're computing convex hull of just G1.
Yes, sir. I'll be computing this.
Convex hull you need with G1 is already
set of invariant regions.
Invariant region, nah? What does it mean to compute the convex hull of that, which I thought which is already in the shape of a polytope.
So I mean, but convex hull of G1 is like, see, this G consists of multiple invariant regions, right? And they might be at different positions. That's why I need to calculate this convex hull G again. For example, look at this thing, this blue one and this blue
what is
square
G1
again.
here? What is G1 here?
This R1 and R2 is G1.
Both of them are G1.
Yes, they are inside G1.
These two things are G1, right?
Yes.
G1. I thought the G was the union of R1 and R2, but you're saying G1. And there are several such G1s. I mean, GI.
Let's say just
yes.
with various different. So, for example, the two whites will give me some G2 then.
Yes. And the other two groups form G2, sir. These two forms G2. So now, since these are not these are at different positions, I am like calculating the convex hull of this entire plane. So this is where the over approximation comes from.
So the reason you want the to do the convex hull is that this collision checking algorithm that you had from algorithm one, you
Yes,
want
yes,
to use that same
yes, yes,
algorithm,
yes.
and that algorithm expects a convex polytope.
Yeah, 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 yeah.
So that is that why you're doing the convex hull, or
Yes,
is
sir. Yes, sir. Yes, sir.
okay?
For to checking the collisions only.
Okay, sure.
So now, suppose
Okay, see, some logistics thing, okay?
okay, sir.
In the
I think
internet,
we are pretty much out of time, right?
yeah, it's kind of, yeah, 11:30, we're getting close to that. But even if I give you 10 minutes, I don't think it will be sufficient. So what I'm suggesting is, this is a very complicated paper, Lucky, okay?
Yeah,
Yes,
This
sir.
is one of the,
this is a difficult paper to present
yeah,
in
it's a
this form.
difficult paper to read, digest, and there's a lot of technical details. And I think you've done, a pretty good job, okay? And
Yeah, I agree.
so what I'm suggesting is that we allow you to give an opportunity to present just the two of us, Diganta and me, to
Yes,
complete
sir.
the presentation later on, and we
Yes, sir.
will ask all the questions and get it clarified to make an evaluation. Yeah, is
Yes,
that
sir.
is that fine? Yeah.
Yes, sir. Yes, sir.
Yeah, but I mean, yeah, sure, we can do that.
Yeah, yeah, I
Yeah.
mean, that is my suggestion, Diganta. Yeah, what
Yeah,
is
but I mean, what I was wondering is how far should we present right now? I mean, should we just stop, or should we at least complete algorithm two?
I
Or
think he has 10 more minutes. He can decide. Okay. You
okay.
want to, yeah, you go through this
I
flow
mean,
chart.
for everybody else who's there, I mean, maybe at least algorithm two,
Yeah.
or
And
whatever.
then,
I mean, there's other people who are interested in this. So,
yeah, I mean, uh, that is something, it's kind of hard.
yeah. I think yeah. So I mean, what is everybody else here?
What do you, I mean, you have this, and then the other algorithm three, and then you have some kind of experiment results. Okay. What do you want to do? I mean, you want to spend the 10 minutes that you have to complete this completely and then present the result. That's one option that you have. Okay. Uh,
Uh,
that might make sense now. Okay.
yes, yes.
Complete
Yeah,
this
maybe.
and then summarize the results, which will summarize the result of algorithm three as well. And then we'll move on. Yeah.
Okay. So, so here I find the convex hull of this thing, and now I execute I check if if this thing collides with uh any edge or not. So it does not. So I get to here. Now I decompose this blue region into 1, 2, 3, 4, 5 invariant regions, and I group together these red portions together. And now, so what happens here is that I detect this one is R4, sir. This thing is R4. So now I detect that there is a collision in R4. So there is a collision in R4, but the thing is, this was not inside our initial invariant region set, right? So this cannot be reached here using my initial region. So I'll have to check whether it is possible to get here by some trajectory in the starting from the initial region. So when I do that, uh, I have this check spurious thing. See if H intersects with E. Yes, I check if that is a spurious example or not. If yes, then I mean if not of that is yes, which implies that it is not a spurious example, then I return that it is unsafe. I'll be coming to this algorithm in the next slide. If no, then I'll remove every vertex which has reached the target region, and then I'll compute the invariant decomposition D of R2 minus T of that. I mean the remaining thing, and then I'll execute my this on this only, and then I'll group regions D, and then I'll put everything in the stack. and this should not be here. Sorry. S equals to stack empty. This should not be here. It should be just add GI to S. So I'll be adding every new group I get into this G after grouping them into D. After removing RT2 to this algorithm is fairly complicated, sir. I can't explain that in such a short time, because then there is this check spurious, which
I see. Okay. But one overall question that I have, how do you determine the groupings? Which ones you put in which group?
sir, like I said, based on the output of the neural network. So, for
So
example,
it's
if
just as long as the network is producing the same output, we put it in the same.
yes.
Okay.
Sir, so what should I do?
No. I think you should summarize what algorithm 3 is, and then quickly for 5 minutes, and then present your results. Okay.
I mean, so
Okay.
what does algorithm 3 do as opposed to
What exactly does it do without
So,
getting into the details,
details.
which you don't have
yeah,
time.
maybe just the goal slide will be good enough.
So this is the prioritized version of algorithm 1. So this is a falsification algorithm, sir. We are trying to calculate to get all possible collisions in the region. Okay. So it uses to prioritize the search paths, searches along paths which are more likely to collide. So this algorithm tries to find as many collisions in a 3D scene of trajectories decided by the CNN. Sorry, it should be CNN. The time complexity is same as the time complexity of algorithm 1, because this is just algorithm 1, but it does returns, it has some priority thing and this collision returning scheme. So what I do is, like, I set my collision equals to 0. I calculate the invariant decomposition D of that, and then I calculate the priorities of this invariant decompositions, these pairs, the tuples in that. So I'll be talking about this priority in the next slide, but assume now that the priority of IM is higher when I'm likely to collide with an object there. When there are a lot of objects there, then this priority of this invariant region is higher. So I'll be using this priority to, in the like similar to algorithm 1, I'll find the next uh, next the next propagation of this R1 that I call R2, and then I'll check if that intersects with any region in E. If yes, then I'll add that to my collision set. Otherwise, I'll just remove that from T, and then if I'll remove all those vertices which have been reached at the target T, and then I'll execute it again, something like that. So it's like algorithm 1 only, but it just has this collision detection scheme. So if D is not empty, like for example, the for loop which we're executing, I'll just return this collision, the set of all collisions. So now, how is so before talking about priority, I'll be talking about potential. Potential is technically the sum of distances of the sum of inverse of distances of n closest obstacles from that. So suppose I have a point and there are like n obstacles which are closer to that, then the potential of that point will be higher, because the inverse of those distances will be higher because the numerator is smaller. So this is this. The potential at point P is given by this formula xi, x1, y1, z, this distance formula of all endpoints, of all close endpoints. So now the gradient of potential, so it's just the partial derivative of the expression which I wrote here with respect to dx. It is like gradient descent only, but it points to the direction of steepest ascent of the, I mean, it's a vector which points where there are a lot of obstacles. So it does that. So this is the visualization of the potential of A. This is A here. This will point to the direction where there are a lot of triangles. So for A, the potential of A is this vector. I mean, this should be here, but for this, I mean, for simplicity and visualization, I put this here. Now, so why do we need the notion of priority? Because
so at a high level, so because I don't think we have time for getting all the details, okay? So at a high level, why do you, okay, this is not a complete algorithm, but
Yes.
see, potentially there can be, it's kind of an under approximation. So it doesn't explore all possible, either trajectories or region. I mean, is it trajectories that it under approximates? And therefore, if there is a collision, then you can report. Otherwise, there is no guarantee that it is, because it's incomplete, you can't say that there are no collisions. Which one is under approximated here? It's the checking method, or it is the possible trajectories?
I think that this it doesn't under approximate everything. This is like similar to algorithm one, so it does check every trajectory except the time. Time is the only constraint here, because I'll be checking all such trajectories, so that will take a lot of time. Yeah, so I mean it will check all possible trajectories, but it will take a lot of time, because in algorithm one, what I was doing is that when I was detecting a collision, I was just exiting. But here I am recording that, and I am now finding all other trajectories and all. So
So is it like so I mean to have create an analogy, is it like a sampler as opposed to a solver, in the sense that it's, instead of just checking whether the vehicle is safe, it is going to return
yes. Set of
a
collisions.
large list of possible
Yes.
safety
Different
violations or
possible collisions
counterexamples.
scenarios.
Yeah.
I mean, given a lot
But
of
why
time,
is this algorithm interesting? I mean, why are they interested in this algorithm? Because
I mean,
what is the advantage of having this algorithm?
this algorithm can be used to check whether a trajectory is safe or not, because it does give a collision at some point.
Yeah, but that the algorithm one will also do that, right? So
Yes.
why did they create this algorithm separately? Is what I was
I think
wondering.
this is for variety only, like falsification. First were verification, so they had to put one falsification. That's the only reason, I think. Sorry.
Or maybe the algorithm too just checks if there is a collision or not. It may not.
Oh yeah.
It may
Probably
not
that.
give you
Yeah.
that.
Yeah. I mean,
Trace.
yes. I mean, yeah, it does return collisions, but I mean, why will I need collisions? Sorry, I couldn't think that.
Okay, I think, is there a summary slide that you have?
Yes, sir. I have a lot of slides.
No.
I mean, it's getting.
I asked you specifically if you have a summary slide.
Oh,
All that
no,
you
sir.
have time for.
I have this implementation slide and then verification algorithms, where I talk about this results and all, and then this related books. I can skip related books.
Yeah, I think we're running very late, Lucky. So we will take this
Sure.
offline. Yeah.
Okay, sir.
Yeah. If there are any high-level questions for Lucky from people.
So shall we? By the way, the next round of presentation, if it does happen, we should probably just make it available for anyone who's willing to join to also be there, right?
Oh yeah. I think it'll be open. Yes. Oh yeah, that's suggestion. I think we should. Yes.
Yeah. Okay. So any
Hello.
high-level questions?
Okay.
Yeah. So, like to add to Diganta's point, like he was
Yes.
asking why algorithm 2, right?
Algorithm 3.
Yeah, the second algorithm, whatever, which is the other algorithm that also gives collisions, right?
Oh, yeah,
So,
collisions.
like it's not directly to you; it's directly to the Diganta as well. Like, isn't this algorithm more exhaustive? Like, it will give you more collisions and than the
I mean
first.
that's true. What I was wondering is, I mean, what do you do with a list of solutions now?
Oh,
Right?
I
Like,
see.
are they suggesting some kind of data set creation, retraining, or do they have some
But
Oh
discussion
yeah.
about?
like
Oh,
if
sorry,
it's
sir.
like if it's
Sorry, sir.
giving more collisions, then it's better for us, right? Like less chance of like misclass, like if it makes sense.
No, I mean,
Uh,
so what do you do? I mean, suppose now what we have is we have a controller and we have this list of huge list of situations where we know that the controller will create a collision, and we know exactly
yeah.
what trajectory it will
Sir.
follow. Right?
Sorry. I forgot this. It was in the beginning of the paper. It said that these are used to train and retrain the model. Sir,
Yeah, I
these
mean, no,
trajectories.
but then I have this follow. The reason that I asked that is that then, of course, the follow-up is that we can always just do some testing instead, right? I mean, we can just always
Yes,
just run a bunch of prioritized testing, and that will probably create a list of collisions anyway. So I don't know if they have some discussion as to why this is better than testing. If the idea is to simply create a data set of collisions, because I understand that if you have a data set of collisions, one can use it for retraining the model and so on.
Yes.
But for that, I would imagine testing would also work well.
Yeah. They don't have such a discussion in the paper sheet. They don't even discuss the testing thing.
Okay. Sorry, Abhinav, you were, I think, saying something slightly different, is it?
Not really, but I think it's fine. I get what you said. So
Yeah, I think we will have, there are a few people who are left, Jnanashri and Maya. So we will have a session and I will schedule that later on. So like Diganta said, we will give extra time for Lucky to finish up, and I'll keep it open for everybody when I schedule Jnanashri and I'm sorry, not Jnanashri, Kathakali. Okay. So now can we switch over to Abhinav so I can.
yes.
So Abhinav will be talking on the third paper on explainability. So it's 11:45. Okay, so 45, 1:15 you'll have to finish to give us time for lunch. 1:15.
Yeah, I think I'll be over even sooner. I should be fine.
1 o'clock.
Yeah. Can you see my screen?
Yeah, I can see you, can hear you.
You can.
Hope everybody can.
Yeah. Okay. Yeah. So I'll be talking about explanations of a model, and I'll start by just. This is just an extension of what Aritra presented. You can hear me, right?
Yes.
Sorry. Yeah, I wasn't sure.
Now it's much better. Thank you.
Okay. Okay. So, what's the motivation for this? It's just that we want to explain what my model is doing. If it's like classifying some objects, it's better if I know how it's doing and what's the like thinking behind what it is doing, so that I can like, because it's like in AI, it's like it's a high stake domain when we're implementing it in the real world scenarios. So yeah. So most most abductive explanations lack formal guarantees of rigor, and they're too large for us to compute and even to comprehend. So this paper introduced a notion of probabilistic explanation, such that
Just
we
a
can.
second, I'm just a bit confused here. You form abductive explanations do provide some guarantees, right?
I mean, yeah, they do, but it's too large, right? Like they
Oh,
do
okay.
provide guarantee. Obviously, they do provide guarantees for us, but it's too large for us to compute them, right?
Okay, yeah, sure.
And it's like, yeah, you won't be able to, like, if you take the whole set, you won't be able to actually comprehend what it means to say that this is an
I presume
explanation.
is computing real minimum ones are computationally very expensive, that you say. The minimum
Yeah,
minimal ones. Yeah.
like a good enough explanation would be too expensive. Correct. So they introduced this notion of probabilistic abductive explanations, and such that they're a little bit easier to compute and uh, yeah. So they give two approaches to calculate these. One is based on this algorithm called approximate model counting, and the other is Monte Carlo sampling. And they give experimental validation on two different models. One is random forest, and the other is binary neural networks. And the experiment shows reduction in the explanation size, so they have a smaller explanations with the good enough with high enough precision. Yeah. So a background on what explanations are.
Yeah, which means that these experiments that they've done, they
Yeah.
don't work for MNIST kind of data, like unlike the
Like yeah, they work for MNIST, but then you only need like two classifications. Like it
so they need to do some transformation to reduce them to binarize neural.
correct. So they can what they do is they take two digit like they reduce the data set into two images, like two sets of classes, and then they use this to like reduce the explanations. Yeah, does it make sense?
Yeah.
And also, I mean, with binaries, the input also has to be in either 0 or 1, right? So
Yeah.
they'll probably do some thresholding on the input images as well.
Yeah. Yeah, they don't really say that, but I assume that they would have this.
Okay.
Yeah. So yeah, so a weak abductive explanation is if we so for an instance V and a classification of that instance into this class C, uh, we say a subset of features is a weak abductive explanation if fixing the features in this subset as same as V, we still get the same classification as V. Suppose we tweak other features except the features that we choose not to tweak, we still get we get the same classification as that, right? Then we call this subset of features as a weak explanation, and we call a subset an abductive explanation if it's a minimal weak explanation. Okay, by minimal I mean if we reduce, like if we remove any feature from this set, it ceases to be a weak abductive explanation. Correct. Now, what's the definition of a probabilistic explanation? It's just a subset of features such that the probability. So if we fix these features, fix the features from this set, then the probability is above some given threshold T. Okay, so this model will classify the given instance correctly with a given threshold T. Make sense? Hello?
Yeah.
Yeah. Clear so far, right?
Sorry, I got
So
distracted.
we're saying that what is kappa here? Can you just explain the notation?
This subset?
No. So the kappa x equal to
This
c. Kappa is
okay.
the classifier.
This is just the classifier.
Okay.
Kappa. Yeah.
So the what
That's
is the
just
probability of the classifier producing this class if the
if we
uh,
just
yeah,
fix the values of my instance X as same as V on this subset,
Okay. Got it.
then the probability of such thing is greater than this given threshold. Okay, and similarly the a PXP is just a minimal
But this
irreducible
is this is
weak.
computed over some set of x's, sample set of x's, the probability, correct? Yeah.
Yeah, so probability is calculated over all the x's that we are not fixing.
Yeah, but that is over all or some finite sample sets. Huh?
No, overall, right? Because like
well,
for the given
for a given x, for a given
yeah,
x.
for a given x.
Yeah. Okay.
For a given chi or like.
Okay. Yeah.
Like if we fix those classes, then the remaining one will be the
Yeah,
will
exactly.
go
So if we
for
fix
all
those
the remaining.
yeah. Should I say that again?
Yeah,
Is
I
it
think
clear?
there was some crosstalk. I don't know why.
Yeah, Ritra was also
No.
giving the definition, but I think there's a little muffling on his end. I can't really hear him.
Ritra, did you have
Oh,
any?
okay. Can you hear me now?
Yeah.
Yeah, like can you hear me now?
Yes.
Like the probabilities over all the if we fix chi here, chi classes, chi features, then the probability is all over the other features.
Correct. Yeah, that's what I also said, I guess. Hello.
Yeah, go ahead.
So if
Yeah,
I
this
just
is clear.
yeah, it's clear, right? Huh? So similarly, we defined a probabilistic abductive explanation if it's like a minimal irreducible weak probabilistic explanation. Yeah. So so they define a locally minimal PXP, which just means that it's just a subset such that it's a weak PXP, and for every feature in this set, if I remove that feature from the set, it ceases to be a weak PXP. In the earlier case, it's a minimal irreducible in the sense if I remove any subset, it ceases to be a weak PXP. But here we are only removing one feature at a time. Okay.
So just to understand this definition a bit better, so previously
Yeah.
when you say you're removing any subset,
Correct.
that includes one feature, right?
Yeah,
So
that does include one feature, correct.
Correct. So
But
is it possible that, I mean, if
correct.
I have a weak PXP, is it possible that I can remove one feature and not have a weak PXP,
Yeah,
but I'll remove two features and it still have a weak PXP?
yeah. So it can happen because we are talking probabilistically. So number of correct classification over the total size matters, right?
Mm-hmm.
So we don't care like if it's always classified correctly.
I see. So
So
because of that, this kind of this
yeah,
property
so
where
the
the weak
monotonicity is
XP.
lost here.
Oh, okay. That is actually very interesting. See.
Yeah.
Okay, sure.
Yeah.
Yeah.
I think, yeah, it would have, yeah.
I'll give you an
pointed out the
example. Just right
monotonicity
now, I'll
is
give you an
there.
example.
In
Sure.
the non-probabilistic case, monotonicity is preserved. Okay. Correct, Abhinav?
Sorry,
So,
could you just repeat that?
no. In the non-probabilistic case, the
Yeah.
monotonicity is preserved.
Yeah.
Correct. Yeah.
Correct.
And therefore, even if you remove one feature at a time,
It doesn't matter.
you are guaranteed to give at least a minimal one. Whereas here,
Yeah.
you cannot guarantee, but nonetheless, they have this as a definition, right? This will not give, this is their own kind of, that's why they call it, give it a new name, locally minimal. This is not exactly minimal. That's what I guess in your key observations you say. Can you go through the key observations, please? I mean, carefully, and yeah, so that if people have questions,
yeah.
especially
So unlike the abductive explanations, as Diganta rightly pointed out, the PXPs are not monotonic. Like removing some features can increase the probability, and soon we'll see an example of it. Yeah, and computing exact PXPs requires analyzing all the subsets, right? Because we cannot afford it to even misclassify one instance. But here we are talking probabilistically. Yeah. So and in the local probabilistic explanations, we are only concerned if removing one feature affects my set of features. So we're not concerned about removing subsets. Yeah, and empirically they say that this locally minimal explanations are often minimal as well. Yeah. So here's an example.
Yeah, go to the previous one. So I want to make sure. Okay, so
Yeah.
what's their goal? I mean, because the monotonicity property is not satisfied, you can't hope to get a minimal one by removing one feature at a time.
So the
yeah, I
thing
mean,
is that like with this definition of probabilistic explanation, like if you're working with the probabilistic abductive explanation, then I need to check for every subset, right? Because monotonicity doesn't really hold it. To enforce monotonicity, they give me this definition of locally minimal.
Yeah, but then you can only hope for getting a probabilistic guarantee of it being minimal. That's what they're saying.
Yeah, correct. Obviously.
So is that clear?
Yeah.
For everybody? Yeah. So they are, this is the best that they can hope for, practically speaking, right? Without enumerating all possible subsets. But if you if you were to enumerate all possible subsets, then you could probably get that with some.
Right. Move ahead. Or is it clear?
But my question is, if
Yeah.
you're willing to pay the price for enumerating all possible subsets,
Mhm.
in this case, for PAXP, will
Yeah.
you get the minimal thing then that you will?
But if I'm willing to check all the subsets, I'd rather compute the actual thing, right?
Yeah.
Like,
Hmm.
like doesn't make sense
Yeah,
that.
but my question was a theoretical question. That's all.
Yeah, you should.
Yes.
Like, it's just a better guarantee of,
Hmm.
like, if you're checking everything, then you should,
Hmm.
right?
Yeah.
Yeah. Correct. So we'll see an example. Let's consider the example. So we're considering this decision tree, and we are evaluating it on the instance this v equal to 2 comma 3 comma 1 written on the bottom of the slide, if you can see. Okay, and this model classifies this as a negative. Like if we see, if x1 is put to 2, we go down this path. If x2 is put to 3, we go down this path, and then x3 is put to 1, and we end up in this state. Okay, so my this decision tree model would classify 2 comma 3 comma 1 as a negative. Now consider this subset of 1 comma 3. Okay, so I'll be fixing my values on 1 comma 3, the features corresponding to 1 comma 3. So x1 would still remain 2, and x3 would still remain 1. Okay, and now if I
Yeah, in the case of first one, 1, 2, 3, you showed that 1, 2, 3 certainly classifies it as negative, but is
Yeah.
that weak also? I mean, if you remove any one of them, it doesn't, huh?
If I remove any one of them,
Is it the minimal? Weak AXP means it should be minimal. If you remove any one of them, it won't no longer will be an explanation, correct?
yeah, because like so it's a weak PXP because if I fix everything, it gives me a probability of 1, right? So and if I remove, so it's not a PXP. I'm just claiming it to be a weak
That is
PXP.
fine. I'm just asking the question, if it is, why is it a weak AXP? Because weak AXP means if you remove any one feature, it should not be an explanation anymore, isn't it? Yeah.
Correct. So let me just see. So if I take this, if I remove any one of
No,
them.
no, I'm a bit confused, but I thought the weak EXP was just that if you fix these features, the classification should be exactly
Correct.
the correct class, right?
No, he sir is asking about the second column. Why
The
is it
AXP column.
AXP?
Okay, okay. Why is
Yes,
it AXP?
AXP,
Okay,
Why is it
Sorry,
AXP?
yeah.
okay, 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 okay.
Yeah,
So it
just
turns
checking.
out that if you change anything, the classification changes. Is it? I mean, change anything else.
Yeah. So if I remove one feature from it, yeah, it shouldn't be, right? Because like 1 comma 2 is not even a weak AXP according to them. Like if you just see below,
Right.
right?
Yeah, since 1, 2, 1, 3, and 2, 3 aren't weak
Yeah,
AXPs,
yeah,
then
Yeah. So
exactly.
I
it
think
has to be
that's
an
it's
AXP.
Oh,
it's a
yeah, yeah.
mistake here.
Okay, I think it is there. Yes, yeah.
Yeah, it's a mistake
1,
here.
2,
Sorry.
1, yeah.
So, wait, so why would, okay. So
No, no, it's correct, right?
It's correct.
it's correct, right? Because every subset is a no, right? So it should
Yes.
be an X.
Sorry. Yeah. Oh, sorry, my bad.
Yeah.
Yeah. It's correct because
Yeah.
if you
The
remove
evidence
even
is
one thing.
there, right there, because 1, 2, 1, 3, none of them is, no?
Yeah.
Yeah.
Mixed up the definition. Yeah, sorry. Yeah, I'll just explain this why 1 comma 3 is a weak PAXP, uh, but and how it violates monotonicity in this case. Okay, so 1 comma 3. If you
And maybe you
fix,
can also explain one of the examples of the third column. Okay.
Yeah, that's what I'm gonna do.
Third column, you okay.
Yeah, weak PXP. Like these two are the same, right? Like this is just telling me when it's a weak PXP or not.
Okay.
Yeah. So if you consider 1, 3, you'll fix x1 as 2 and x3 as 1. So x1 is 2, we go down this path, and then x2 we can choose. We can go down here. In this one case, one possible scenario, it will classify it as positive. And if we go down this path. Then in these 3 cases, it will classify it correctly, and this one case it will misclassify it. No, oh, sorry, we are fixing x3 here, so it'll always go to this. So out of these 5 scenarios, out of these 5 scenarios, only one misclassifies. So 4 out of 5 times we get a correct answer, right? Did you follow?
Yeah.
Hello.
Yeah,
Yeah. So
that makes
sort of,
sense.
so 4 out of 5 times I get correct. So I'm taking my threshold to be 0.7, and in this case, I get a probability of 0.8. So it is a weak PXP. Yeah.
Yeah.
Now
Yeah.
you see that even removing uh, uh, yeah. So if I remove this feature 3,
Then you get a lower probability, right?
yeah, we get a lower probability. But so I want to show that it can increase the probability, right? Like in excluding something
Mm-hmm.
can increase the probability.
Right.
Just a second. I remember seeing
So are
an
you
example.
still working with this S being 1, 3?
No, I already explained why it's a weak PXP.
Yeah, that you did.
Yeah, correct.
But why is it?
Just a second. I seem to have lost the thing that I was gonna say.
Why is it not a PAXP?
Oh, yeah, correct. So why it's not a PXP, right? Because if I remove 1, if I remove 1 from it, 3 is still a weak PXP. So it's not really a minimal thing. So
Sure, but I mean, so what we want is something that is uh,
I want to say that 1, 3 is not minimal, not a minimal weak PXP.
Yeah.
correct. So that is fine. I mean,
This
Yeah.
is where the monotonicity is being broken.
but we still don't see monotonicity being broken, right?
Yeah. So monotonicity being broken would be that if this given set is classified as not being PXP, but a subset is.
Yeah,
But
and
a
for that
subset.
we would need the probability to increase.
Yeah. Yeah. So correct. So look at this 1, 3,
Hmm.
right? 1, 3, it's not a weak PXP, right? Because I just showed that 3 is also 3, which is a subset, is a weak PXP, right?
Right.
But you can see that this set 3
Hmm.
is a PXP. So a subset of this uh, uh, so 1, 3 is classified as no, but a subset is classified as yes in PXP. This is where the monotonicity is broken, right?
1, 3, 2, 3. Yeah.
1, 3 is classified as no.
No,
But
but
3.
what 3, a subset, a smaller set, is classified as yes. So I would accept a 3 as a explanation, but I would reject 1, 3, which would not happen in a normal scenario, like in the case of abducted explanations. Every superset is also an explanation.
Correct.
So here the monotonicity is broken.
But yet the probabilities are monotonically decreasing.
Oh no, we don't care about that, right? We
I
only
mean, we don't, but
okay. I mean,
yeah.
we could conjure up some example where this happens. I don't really
The
particularly have
probability
an
also
example in
flips.
this.
Yeah, sure.
Yeah. But yeah, I can conjure up an example and probably send it to you if you want.
Sure.
But certainly for a fixed threshold, it is not. It is non-monotonic, right? Yeah.
Yeah.
Hmm. But yeah. Hmm.
Yeah. So
But that's interesting, Diganta. You asked that question. Okay, so you could have another kind of a definition where if it is another kind of monotonic definition that the probability is increasing,
Yeah, but even that will probably not be
will
monotonic
not be
is
true.
what
Will
the,
not be true because it can
yeah.
up and down in whatever.
I think, I mean, yeah, I mean, I'm
Yeah.
willing to believe so at this point, but
Hmm.
yeah.
If probabilities are monotonically increasing, then like locally minimal and subset minimal will be the same, right? So it's not. No, I get the part, maybe, but like, what do you
No,
mean
but
by
see, here
probabilities are?
that is what I'm confused about as well. So because here the probabilities are monotonically increasing, right? I mean, each subset has got a strictly lower probability than its supersets.
hmm.
Oh no, that's not the case actually. Actually, we figured some example. Actually, we conjured some example up, but like the thing is like if that's the case, then locally minimal and subset minimal will be the same. But that's not true, right? So the probabilities will not always monotonically decreasing or increasing for superset or subset like that.
Okay.
I think so at
No,
least.
but why do you say that if okay? So what? So I still don't understand actually what's going on here. Here we are saying that 1 3 is not a PXP because
A subset of it is a weak PXP, which
For
correct, which
that
is 3,
threshold. For that
yeah,
threshold.
which is 3.
yeah,
So since 3 is a weak PXP, 1 3 is not a PXP.
correct. But 3 is just a
I
minimal thing because it's
see.
a singleton set. It has to be a PXP.
Good, of course, yeah.
Yeah.
Right. Okay.
I am not sure what's the difference between PXP and LMPXP. Are the same?
No, no, no. So in PXP, you can remove any subset of features, but in LMPX, you are only
Okay.
allowed to remove one feature at a
I
time.
see, I see. Yeah, yeah. So, oh, that PXP subset minimal PXP. Yes, yes,
Yeah,
yes.
correct.
So they are different. Like in this case, they are not like there is no instance for that, but in general they might not be same. Like
Yeah.
let's say you can remove one feature to keep it as LMPXP, but you can actually remove two features to make it a not make it a PXP like that. So like the exactly the monotonicity is not conserved here.
Hmm. I see.
Like I think you can just conjure up an example, something like
Yeah, like
one
yeah.
side of the graph would just misclassify everything or like classify it correctly or something like that. So removing something would just increase the probability of getting it correct by a lot.
Yeah, sure. I think maybe we should, in the interest of time, keep
Yeah,
moving
yeah.
or
Okay.
yeah.
If you
Yeah,
want,
yeah.
I can send you.
Very-
Okay.
Yeah, no, do send this example. I'm still not completely digested it, but yeah, I think
Okay, okay, sure, sure, sure.
The example that you want is that where
the probabilities themselves are non-monotonic, right? So that's what you're talking about.
Yeah, yeah, correct. Yeah, okay. So,
wait a minute. I mean,
yeah.
there are two other things. Okay, why don't you? What is min PXP? LMPXP you explain.
Yeah.
Min PXP. Oh,
It's just the subset minimal PXP.
yeah. I guess you cannot. Okay, you can check if it is or not by doing it, but you cannot get to it by removing one.
No, so min PSP is the
No, no,
minimal size minimal PSP,
minimum,
right?
yeah.
Yeah, minimal
No,
size.
minimum size PX, not minimal, I
Minimum
think.
size PSP, yeah.
Yeah, but
Yeah, like min PXP is the minimum size PXP, not the minimal.
Right.
Minimal
That
one is the
minimal one is
like
Yeah,
PXP.
yeah. Sorry, my bad.
yeah,
Yeah,
yeah.
minimum.
Yeah, yeah. Okay, okay.
Yeah,
Sure,
just
sure.
mixed up the
That
two.
makes sense.
Yeah.
yeah, but my point was that even that you cannot get by removing one feature at a time. Okay, you cannot do that, no?
No,
Yeah. Huh? That was my question.
that won't make sense, because if you remove it's possible that you can remove two features. No, yeah, sorry, could you just repeat what you said?
Can you compute
Huh?
in PAXP
Yeah.
by actually checking by removing one feature at a time?
Um, uh, no, I don't think so. No, no. It can so happen that in this order, in this particular order that you're removing your features,
That's right.
you
Yes.
can just remove a feature
Mhm.
uh, such that it doesn't allow the other two features to escape. Yeah. Okay. Should I move? Should I move on?
So
Yeah.
sorry,
Yeah. Yeah.
just one question. So when the monotonicity violation that we were confused about
Yeah.
was whether weak PXP is subset minimal or not, right? As in, if we have if we have a set S which is a weak PXP,
Yeah.
will all its subsets will all its supersets also be weak PXPs, right?
Okay.
That is, I mean, if that is the case, then LMPXP and PXP should be the same.
Yeah.
But the claim was that that indeed is not the case, right?
Yeah.
Yeah,
But
That's
that
this
could be,
table
yeah,
doesn't
that
show an
might not be the
example of
case.
that, right?
yeah. Uh,
Am I?
yeah. Yeah. You're making
Is what I'm
sense.
saying makes
Yeah.
sense, or am I saying something?
Yeah. What you said, like if a weak PXP subset is always a weak PXP, then like locally minimum and subset minimum will be the
Yeah.
same, right?
That is
But
correct.
it
Correct, correct.
isn't the case
And in
always.
this
So
Yeah.
case, at
That's
least all the weak PXP supersets are weak PXP. So that example is not there in this table, at least, right?
mm, no, right? So let's look at this example of 1, 2.
Okay.
1, 2 is a weak PXP,
Yeah.
but the subset is
Yeah. No,
not.
the other. I'm not. I'm
Oh,
talking about
sorry,
the
sorry,
other way
sorry. The
now.
superset. Sorry, sorry. Yeah. Sorry.
Yeah.
Correct, correct.
So,
So
for example, 3 is a weak PXP, 1, 3, 2,
yeah,
3 are
correct,
weak
correct, correct.
PXPs.
Yeah. In this case, they don't give an example of that.
Right, right. Because I mean, if that is the case, that I mean, if weak PXP is not monotonic, then you need to do LMPXP. Otherwise, LMPXP and
Well,
PXP should be
else
the
they
same.
would be same. Else they would be same.
Yeah. So that's another example, okay, to
Mhm.
ferret, no? Yeah.
That's the
Yeah,
exact thing that
if you have
what
something,
Diganta want.
or
I
Yeah.
don't have
That's
it
the one
on
that
me
you
right
want.
now, but I can surely send it to you.
Okay, sure.
right.
Please.
I mean, as in, if it's in the paper, or if you're able to figure it out. If it
It's
is
not
not
there
in
in
the
the
paper
paper.
and you're not able to figure it out, then we should probably just
You
mail
know,
people or something.
I remember doing something, but I don't
I
exactly
see.
remember what I did. So I'll think about it again and send it to you.
Please circulate. Yeah.
Yeah,
Move on.
yeah. So now what they do is like they want a Boolean encoding, like a pseudo Boolean encoding of my binary neural network, because they'll be experimenting on
Yeah.
this.
Yeah. I think the audience, I have not in my course covered pseudo Boolean encoding.
Uh,
Yeah,
didn't we
just
get an assignment on
explain. I mean, once you explain what it is, it'll
Okay, so here your variables are Boolean, and your coefficients of the Boolean variables can be integers, and your constraints are also can also be integers.
yeah,
Okay,
coefficients and B, both of them can
yeah,
be.
can be integers, and these sort of constraints are called pseudo Boolean constraints.
But in binarized neural networks,
Yeah.
even the weights can even be reals.
Even the no, in this case, I think weights are binary.
Yeah, weights are binary. Whereas here, as a pseudo Boolean constraint, you're allowing weights to be anything. Okay.
Yeah.
Yeah. Okay.
Oh, this is a typo. It's WI, not CI. Sorry.
Yeah, just for the rest of it, this one is you can always encode. Okay, this is this compact encoding of you can always have these things encoded using in some cases, I'm going to say always. I mean, I think I'm pretty sure as using cardinality constraints, but nonetheless, it gives power of very compact constraint when compared to purely propositional encoding. Yeah, I just wanted to.
What do you mean by cardinality constraints?
No. There is a way, there is a big literature as to how you could encode, convert, transform these kinds of pseudo-Boolean constraints into equivalent propositional constraints. Okay?
Okay, so converting it to a SAT, right?
To convert it into a
Yeah,
SAT.
yeah. That's what
That
they
is where you
do.
could use
Uh,
cardinality constraints
I see.
of certain sets and so on. So
Yeah.
it's fairly well-studied thing. We do.
Yeah. At the end of the day, we are only concerned about the SAT formula that you're talking.
That's right. Yeah.
Okay, so but I won't discuss how do you do
No.
that
You don't
here.
need to. I mean, because
yeah.
these are compact encodings can always be discharged using SAT, which is what they do eventually.
Yeah. So so this is nothing but just ensuring that my neural network, every neuron in my model is working correctly. So what it means is that if my output of my neuron is
With
say zero,
ReLU, I presume. Yeah.
no, here the activation is sigmoid, sir.
Sigmoid. Sine. Correct. I got it.
Yeah. So if my output is zero, uh, I want this constraint to be negative, like this sum to be negative, right? Then the signum would output a zero if it's negative. If the value of my node is negative, then only it will output a zero. Correct? And if my node is one, I want this constraint, this sum to be positive, because then the sigmoid function will output one. Yeah, so that's how I just encode every internal neuron. And for output neuron, I just say that suppose yk is the Boolean indicator that the class ck is dominating class cj. Okay, and uh, sj is just the indicator that the class cj is selected. So what I want to say at the end, at the output layer, the weights, the output corresponding to uh, the node that selects a given class, uh, s- uh, class cj, should be less than or at should be less than the output of the neuron that selects the class ck, because we want ck as the output. Okay. Hello.
Yeah.
Yeah. So this is just
I understand if there are any other questions from the audience, because I've seen these encodings. Yeah, I can believe that. Yeah.
yeah. So this is just a sanity check of my each neuron is just working how it's supposed to.
Any questions here? Yeah, the linear layers, because of the restriction on the weights and x and y, they are already can be expressed as pseudo-Boolean constraints. Correct? Yeah.
Yeah. So I'll move on to the second part where they give a encoding of a random forest. This is also just saying that uh, for all paths, for a path in P, uh, if we go along that path, it classifies as PJ. And how we select a class is by taking the majority voting over these ensemble of trees. If if there are if there are greater than k many trees, that actually classifies the instance as a given class. Yeah, this is just saying that. So I'll move on to the second, so the main algorithm that they give. This is not the main algorithm, sorry. This is one way of counting how many uh, how many instances are correctly classified. Okay. So this approx model counting algorithm, so given a SAT formula, this gives an approximation of uh, uh, how many satisfiable assignments are there for this formula. Hello? Any
Yeah.
questions? Yeah, any questions there?
No, but I
Like,
think we should go through that thing. I mean, what is approximate model counting? Fine.
yeah. Okay,
Okay.
so how this algorithm works is it divides your input space into a bunch of cells, into small enough cells, and it goes on and goes on checking if this goes on counting the non-empty sets, such that in each cell there is a if there is a SAT formula, it puts the cell in my basket.
Yeah, but you missed one. I mean, they for a particular sampling, right? So they sample the input space and then partition. No, yeah.
Uh, no, in this case, they're not sampling the input space, right? Here what they're doing is,
It was approximate model counting. Model counting, yes.
yeah. So what they do here is that they
Okay.
divide your input
Sorry,
space into a
I'll
bunch of
let you
cells.
speak. Yeah. So first define what is model counting, and then how do they do? Model
Okay,
counting is just counting the number of things. So here,
so
why is this
yeah,
approximate? Yeah. So they
yeah.
will
So they
partition the
approximate.
entire input space into, and I mean, yeah. What
So
do
it's just yeah. Sorry, Diganta, were you asking something? Hello, was there a
No, I
question?
was not asking anything.
Okay, sorry.
Natalie has unmuted me.
Oh, I see.
they?
Yeah,
I didn't ask anything.
yeah. I'll go ahead. What this approx model counting does is it gives you, so given a SAT formula, it will give you how many satisfying assignments it has. So it doesn't give you an exact number of satisfying assignments, it just give you an epsilon approximation of on the true count. Okay, and how it does is it divides the input space into small cells, and it goes on counting the number of non-empty cells. So it can so if it finds even one satisfying assignment from a cell, it puts a tick mark on that and puts in the basket. And uh, so this is how it goes on to counting. uh, so now it just multiplies your total number of cells multiplied by uh, uh, just a second.
So it
Yeah, size of the cell and the number of accepted cells.
so it
This would
doesn't check that for every element in a particular cell, every that it is true. Huh?
correct. So it
Yeah.
just takes the whole set given on just one representer of that cell.
How was the cells partitioned? What criteria is used for
I'm not really sure about that. I think it's really it's a heuristic. It depends
yeah.
on what you
I mean,
want.
intuitively, what
Yeah.
is this thing? I mean, somehow they have to be closely bunched, I think, no? So, or what is it? How do they do it? That is always thing. I
Yeah.
mean, do they use some kind of a
It's again
distance heuristic? But distance heuristic may not work. This is yeah. They I guess they do some distribution or something. So that is always one question that I had, which is
yeah, you could use different distributions and then maybe pick the best one.
yeah, okay.
Yeah, no.
But anyway, they use this as a black box here. So I guess in this paper that they have not discussed it, right?
Yeah, here they use this as a black box, correct? Yeah, so this just gives me an approximate number of satisfying assignments for my given formula. And so this would help me calculate the probability that I want, right? So this eta star is exactly the eta is exactly the is the numerator for my probability computation. These are the assignments that correctly classify uh, my instance, and while keeping this same, right? But instead of finding eta, we get an eta star, which is a good enough approximation of this. Okay. Yeah. And similar, a second approach would be this Monte Carlo sampling, where this is nothing. Here they fix everything that we want fixed, and uniformly sample every other feature. So that the features that are not fixed, they are uniformly sampled. And by Hofstadter bound, we are sure, we can say that if we sample these many times, then we can be be in an epsilon ball of our desired count. Okay.
Oh, I'm not sure I understand this thing.
Okay. So yeah,
Yeah.
I'll explain. So assume xi.
Hmm.
Xi is your random variable such that it is 0 if your ith sample is uh, is not a desired candidate, and it is 1 if it is a desired candidate. And by desired candidate, I mean that it correctly classifies it.
Hmm.
Okay. Yeah. Hello.
Yeah,
Yeah.
desired candidate in the sense that's a subset of the feature, huh? Yeah.
Yeah. So what I'm doing is I'm fixing the features in my chi, right? Like this S,
Hmm.
this subset S. I'm fixing the features in S, and everything else
Hmm.
I can tweak.
Hmm.
So how I do it, I uniformly sample everything
Hmm.
for the features in this set.
Hmm. Hmm.
So now, so for the ith trial, xi would give 0 if this whole set of features is correctly classified,
Hmm. Hmm.
and 0 if it's not.
Hmm.
So what I exactly want in this n trials, the
Hmm.
sum would give me the number of things that are correctly classified, right? Hello.
Yeah, yeah.
Yeah. So and
And the number n trial is here the sample size, right?
yeah.
Okay.
So
Here
I'm
you some sample
yeah.
size. Yeah.
So n times I'm trying to find the correct answer, uh, and the sum over these random variables would give me exactly how many times I was successful in finding a satisfying assignment.
Yeah.
Now, the Hofstadter bound says that if I want a good enough approximation, like if I want to be in the uh, in an epsilon bound of my uh, true probability, like if I were to check over all the samples, and if I want to be in a epsilon ball of that, I just need to sample at least these many. Then I'll be in a close enough ball such that I can just stop there. I don't need to check over the whole space.
So ultimately, both of the methods are estimating probability with pack guarantees.
Yeah, correct. Exactly.
Okay.
Because our algorithm just uses this number of approximations
Yeah.
to reject or accept a given
Yeah. I mean, yes. Now here there is this real sample size. But there in the other one, approximate model counting, do you remember? I mean, I thought that, they partition the entire input space. That would be very hard to do. I mean, do they also use some sampling methods there?
So I don't know what they do, but I know that
No,
for example, Professor
obviously
Priyanka
they
Golia has a tool uh, which uh, which does do some sort of sampling based things as well.
excuse me, sorry.
Yeah.
So
I think
obviously they'll need some sampling, right? Because after
Yes.
dividing up into cells, they're sampling from the cell and checking if the cell is supposed to be accepted or not. So that's where the sampling comes in.
Oh, I
But
see.
why do we need cells in the first place? I mean, maybe this is a detour question, but yeah.
No, I mean, it's not that hard. Like, so they're trying to approximate the number of solutions, right? So how they do is like they divide the input space into a bunch of cells, And if there is if they're successful in finding just one correct satisfying assignment from a cell, they take the whole cell.
Okay.
Okay, so they say that this whole cell is accepted, and these are the whole satisfying assignments.
So I think it's very critical as to how they determine what they put inside each cell.
Yeah.
Yeah, and or at least where they draw the line separating two partitions. Okay, and that is the question.
This, so
Yeah,
this algorithm then would not need any kind of sampling, right?
this doesn't. Yeah, it's not.
As
Sorry.
in, when I say sampling, what I mean is something like some kind of SPIT or some resisting based.
No, this would, right? Because how do you check from a cell which cell to accept? Like you would sample from that set and check if it satisfies, and on basis of that you
Okay,
accept or
okay,
not.
okay, 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 okay.
And so the sampling is required.
Okay, 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 okay. I see, I see. So basically, then what we are doing is instead of just simply so in algorithm,
Sampling over the whole space, you
right, we're just
divvy
sampling
up
over a
one to
slight
correct.
abstraction, which is these cells.
Yeah,
So number of cells is still large enough where you need to actually sample and you can't enumerate.
yeah. It's a trade-off between how big your cell is and how
Hmm.
yeah,
Hmm.
how good of an approximation you want.
Right.
Yeah. Yeah, so these are two ways of actually predicting your number of
Yeah. So
satisfying
in the
assignments.
approximate, sorry, I'm belaboring on it. Now, the approximate model counting,
Yeah.
the number of partition is also a parameter, no? So you could
Yeah,
how
yeah,
determine the
yeah,
number?
of
Yeah.
course.
Yes. Yes. Yeah. So there's also that thing as to it has to be not too small, and it's too large. It is.
Yeah, that depends on my epsilon and delta, because how good of an approximation I want would determine the size of the cells. It's encoded in these epsilon and delta.
Yeah. Okay. So I think now it's clearer, Abhinav.
Yeah.
Thank you.
Yeah. So how they go about finding locally minimal PXP is they just start with
The
this
rest of the thing is how they use.
yeah.
I guess they use either of these things as a black box. The
Yeah.
algorithm for the thing is the same, and it only matters in terms of experiments, right? Which
Yeah.
Okay.
Correct. So how they do is they start with the whole set. We know that it's a abductive explanation, right? Or we could just start with any other abductive explanation if we have, and we aim to reduce the size such that we end up with a locally minimal PXP. Okay. So how they do is it'll be remove features and like till while the weak PXP condition is satisfied. So they just assume that they give an explicit order to your features and they start removing it one by one. And how we remove is dependent on how we count the if the weak PXP condition is violated or not. Yeah, that's it. So I'll just explain the algorithm here. So given a model, a classifier, and an instance, and the correct classification of it, and a given threshold and epsilon delta, we want a subset of features such that uh, it's a locally minimal PXP. Yeah. So how they do it is they start with the whole set. They encode this condition that my classifier classifies a given input as C as a SAT formula. Now for each feature in the features in this F, what they do is they start removing it one by one. Yeah. Now they remove. Okay, here you don't need an explicit order on the feature. Sorry, my bad. You can just start wherever you want. Doesn't really matter in
Anyway,
what
it's
order you
not
go.
monotonic. No. Yeah.
Yeah, that's why you don't need the order. Sorry, that's what, because you can just start anywhere. Yeah. So they calculate they calculate this SAT formula where we want to fix all the positions in this set S as my given instance V. right? Except at position I, except at feature I. So I'm fixing everything except the feature I. And now I use my counting algorithms to count the satisfying assignments. And uh, and the probability is just the number of correct classifications over total number of points that we sample, that we need to check, because it would just be the size of each feature space, like just a product of all the feature space except the ith feature.
And here
Right.
they use the same sampling as they. I mean, yeah. So
Here we are not sampling.
no. But they'll have to. But this is an invocation to those
Yeah.
it's not.
Correct.
Yeah.
Yeah, it's just an invocation.
Yes.
So yeah,
Oh,
here
no.
we
Here they're not using, but in the previous step, and start is approximate count.
Yeah.
There, it uses its own whatever sampling.
Yeah, it's all contained in this one line, right? Approx count handles it all.
Yeah, but
Yeah.
the denominator here, how is it computed over
This detail?
those sample set that is used there, or it is all?
No, this is just the set of features.
I'm sorry. Yeah, once again, I'm confused. Yeah, it's just the feature set, and then you fix certain values, and then for all the other possible things. Yeah.
So these are the feature sets that are not fixed.
Yeah.
Yeah. And if this probability is greater than the given threshold, then we just remove it, because this smaller set is also a weak PXP without the given ith feature. So we accept it as a, like, this smaller set is accepted as a weak PXP, right? Else we don't remove it. And doing this, we just get a locally minimal thing, because removing any one element would not let this be a weak PXP anymore, according to this algorithm.
Any questions here? The pro, anybody? You have any?
Not really.
Yeah, should I just move forward now?
Yeah, please.
Yeah, so now it's just experiment results. So they run it on different data sets, right? And the average size of their abductive explanations is around 5.6 for like, these are just data. I can't really, there's nothing much to explain here, but yeah. So there's a reduction in the size of the explanations while the precision is quite high. Okay, so what we want from our what is a good enough explanation, right? A good explanation should be a really small set, such that anything that is outside of it changes and it still doesn't affect my classification, right? So this gives me a good enough reduction in the explanation size.
First, I have a question about the benchmarks.
Yeah.
What do you mean by data set? These are different network represented as, models represented as random forest. Why do you call it data set?
No. So my classifier is a random forest, and it's used on the data set named this. It's just my classifier is a random forest. I'm using
so there is a particular model, the classifier that is represented as random forest, to which you are feeding different
data.
Sets, the X capital. The data set would determine the X. Huh?
No, I think it's that there are 6 different classifiers, each being trained on adult agaricus German.
They're just trained on those things.
Yeah. Is that understanding correct?
I thought that was understood, that we are training everything on.
So the
like
same,
the same model, but like different
same
trainings.
model being trained on different data sets. Okay.
Yeah. Correct. Yeah. So they just show that we get a really small explanation size and a good enough precision of my models.
No,
Yeah.
no, the reason I asked that question was because usually, yeah, people vary the DN, and here, I mean, it is,
So implicitly, the DNN is varying in the sense that
it is varying
if you're
because it's
doing,
being trained to do different
yeah,
things.
Yeah.
Okay.
yeah. So the actual decision tree will look different in each of these decision
Correct.
forests.
Yeah, but only the structure will be the same.
I
Some
mean,
So even the structure can be
structure
different. The
being the random
predicates will
forest,
be,
like the general structure, yes, but
ah,
not like local.
yeah. I mean, as in all of them are random forests, so they'll look like some kind of decision trees, but
Correct.
the actual connections might be different because they're trained on different data sets.
connections and
Weights and all,
yes, the
everything would be
weights. I
different.
mean yeah, how they query, etc., will be different. Yeah, can be different.
Yeah, this is just to show that it can handle like different kind of data sets, like just that.
Okay, go ahead, please.
Yeah.
Yeah.
Yeah. Second,
No,
they
no,
they
no,
give.
no.
Yeah.
Can you complete that?
Sorry.
Yeah, because we got sidetracked.
Yeah.
What
Like
are you explaining?
w-
Yeah.
what exactly would you like me to explain in this?
No. What is
It's a
the
very self.
takeaway? Key
Oh,
take.
it's key takeaway. Like it's just that it gives me a reduction in the size of my explanation, and I would want a smaller explanation because that gives me higher generalization power, right?
Can you explain that point a bit? Because how do we know that a small explanation? I mean, in the sense,
So
is it true that it's
if I have a small enough explanation for my model, right,
right?
it means that it's not quite dependent on the whole set of features.
Right. So what?
So
Yeah. So if I get
so
a
it's
small
not really
weak,
it's not learning everything according to my data set. It's actually like you you
at
see
least
what I
this
mean, right?
particular decision.
Yeah.
Right. Yeah. So okay. Yeah, I see what you mean.
You see what I mean, right? Because like it'll have a higher generalization because um there are uh, how do I explain this? So
Yeah, because see, in the case of formal like AXP non-probabilistic situations, there, of course, since we have monotonicity,
yeah,
there is this notion of the strength of an AXP, and from that point of view, the smaller ones are stronger, strictly speaking,
correct.
right?
Yeah,
But
exactly
that is
same.
not the case here. I
Uh,
mean, yeah, I mean, it's not necessarily the case here. So then,
no,
uh, but yeah, I can see what
I
you're
mean,
saying.
it's
That,
similar here. It's just that you cannot deduce anything about a smaller set from a bigger set, but a smaller
yeah,
set in itself is a good enough thing. That inference doesn't really shake, right?
right. This the smaller set is talking about more of my potential input space in some sense.
Yeah, exactly.
Yeah.
So that inference is not really disturbed.
Yeah, that makes sense. That makes sense. Yeah.
Yeah, correct. So yeah, I'll move on to the next part. Here they train here that model is the binary neural network, and they train it on this reduction of MNIS, where they take 0 and 8 as the classifications and like they just choose two random digits and use them as
Some digit
classifiers.
recognition thing.
Yeah, correct.
Mhm.
And in this case as well, they see a reduction in the explanation size, and it's like computation is also uh, computation time is also quite low. It's like they are practical runtimes with high enough precisions. So say they take t to be 0.99, which means that any set is accepted if and only if it's the probability of it correctly classifying is greater than 99 percent, like 0.99.
Yeah, these high precision numbers are how the level of confidence one can get. I mean, that's what I
So what does the precision mean precisely over here? I mean,
that the probability, I think. See, the
Yeah,
key is the threshold
the
probability.
precision would mean that like in the terms of threshold, it means the probability of my model correctly classifying when I fix these.
Correctly
Uh,
being an explanation. Okay, that's what it means.
yeah, correct.
Yeah.
Correct.
also the threshold is in the 0.99. Okay, that's what the high precision means.
So
Yeah,
it's very high. But
Yeah, but then there's also, see, the reason I'm asking this is because there's when you're computing weak PEXPs via the model counting procedures, the approximate model counting procedures, what we are getting ultimately is a pack guarantee on the probability value coming out of the counter, right?
Yeah,
Correct.
correct.
Which means ultimately, when I'm estimating or when I'm checking whether or not that probability coming out of the counter is greater than T or not, there is an underlying probabilistic guarantee on that check being accurate or
Correct.
not, right?
Correct.
So even though they're saying that, okay, so whenever they're saying that this is a weak weak PXP, with respect to this threshold, there is a probability associated with that statement as well, right? So do they talk about what that probability was?
No, they don't. But
Right.
again, we can just like bump up my epsilon. Like I can reduce my epsilon so much that I get a good count. Like it's just
Yeah,
that
yeah, yeah. You can do that with the epsilon, but then you'll still have the delta left over, right?
yeah. But yeah, it's
And
just that
then,
these epsilon deltas are there just to reduce the time, right? Like they
sure, sure, sure.
obviously ensure the precision. I agree.
No, no, but
But it's
I'm asking, are they are they sort of folding the delta into the decision somewhere, because that's not there in the algorithm, for example, right?
yeah, it's not. They don't like they don't give an explanation of like they don't explore this
Talk about that.
like probability inside this probabilistic argument.
Yeah, because I mean, it's so suppose we get the some. So if I'm understanding things correctly, we're
Hmm.
getting some probability out of the counter,
Yeah,
and that probability we know is you know,
approximately correct.
yeah, it is some pack guarantees on that, right?
Yeah,
So we know
correct.
that that is the probability that output probability is epsilon close to the actual thing is at least 1 minus delta. That's what
Yeah,
we know, right?
correct.
Now let's say that I've chosen my epsilon. So epsilon and
Mhm.
delta are hyperparameters to make counted. I've
Yeah.
chosen my epsilon so that even if this output probability is epsilon close to my actual probability, I've
Hmm.
chosen my epsilon such that based on that I can take the decision. So like if the output probability is greater than equal to threshold plus epsilon, then I say that my original thing is greater than threshold, let's say, right?
Yeah.
So that's what you mean by bumping up the threshold, if I'm understanding it correctly, right?
Yeah. I'm okay.
Yeah, but then the delta still remains, right? So now what I know, even if that decision goes through, I know that okay, my original probability, my output probability is greater than threshold plus epsilon, which means with probability 1 minus delta, my original probability will be greater than threshold, right?
Hmm. Yeah.
Yeah, so that delta, I was thinking about whether one can fold that into the
Okay, in the bigger probability, like the
yeah,
large
somehow, but it's not exactly clear. I mean,
total
if that is,
probability.
I mean, one can, what would that
It's
even mean and so on is not very clear to me
yeah.
at least.
No, no, but
And
another related thing for your question is what does it mean? They give certain pack guarantees, okay, but that applies for all applications. Why? It is not application dependent. It is somehow that is those guarantees are there for the technique itself, no? So
yeah, no,
how
I get
what
that, but I
use
mean
would
that
that
will
be?
factor
I
into
mean,
the precision, right? So
yeah,
when they're saying that it's
it
So
sorry, go on.
factors into
so
the
he's just saying
precision.
that don't
Yes.
be too happy about the results because they're not exactly what they claim to be.
No, I mean it makes like that would be a more interesting detail to know
No, but
about the
to
results, right?
me, more interesting is to understand what are the parameters that determine the inherent basic pack guarantees that they give,
Hmm.
then fine tune that into this thing to see if I can get improve the effectiveness of the method itself, and then how it impacts on this for any given threshold, how much reduction I get and with what accuracy and so on. Huh?
Correct, correct.
Yeah.
And how does
Yeah.
the time vary with that? That is basically what my
Yeah, so I think that what Diganta is asking, like, can we tweak our threshold in some way so that I can ignore the pack guarantees, right?
yeah.
That's what you were
But
asking, right?
that is what I was asking, right? But
Yeah,
and then then it's not a factor of do we want? I mean, so right now we are saying very high precision, but it's not clear what that means because the delta is not given, and
correct.
we are saying that okay, it's practical runtimes less than 300 seconds, but it's not clear what that is giving us because maybe if we want truly high precision with a truly low delta, the runtime will have to be much higher for because the counter will take longer, right?
Yeah.
But if we are able to fold all of these things in, then we'll have to force the algorithm will have to force the counter to run as long as it needs to run to truly get me whatever threshold I'm looking for.
Mhm.
And even then, what we have is a probabilistic result, because we're talking weak A
No,
space got the
here
probability into the
they
definition
obviously
somehow,
take
right?
some values of epsilon delta, right? So
Correct.
I haven't written them here, but yeah, they work with
So
some.
what values of epsilon and delta are they working with?
I don't remember exactly. I'll have to
Sure.
check. Yeah. So
Yeah. Does that make sense?
yeah.
So you're actually saying that you're pulling up those epsilon delta and making it parameters of this T, huh?
Yeah, I mean, I'm thinking whether that
Yeah,
should
but
be
that
possible, right? Because then now we have got two like kind of free variables fighting with each other. Like we can choose an epsilon delta gets lower time, but then what is how do we interpret the precision? Or we can choose a high epsilon delta and get a very high amount of time, but do we really need to do that? Either of those two things are not clear.
Yeah, but then, I mean, it's worth asking the authors, because anytime you do that, you're taking the epsilon and delta, and then there is some echo.
Yeah. I think I just my earphone ran out of charge, so
Yeah.
just give me 1 second.
So does it require does that probably that makes somehow configuring these tools for each epsilon delta and then running the experiment will be harder? Yeah.
Hmm.
But
Yeah, of course, if you're like bumping up your like if you're decreasing epsilon and increasing your guarantees, like the delta,
Hmm.
like you'll obviously require more time, right? Like, like that's what you were saying, right?
no, but does it even require these tools to be configured? No, for different epsilon delta? No.
What do you mean by configured here exactly?
I thought the epsilon delta were kind of fixed in this case, or that was
No, there are parameters for your approximate model counting thing.
well, that is what I'm saying. If there are parameters for the approximate model counting,
Yeah.
do they in these experiments they must
Yeah, they fix them.
fix
Correct. They
But
fix
why
them.
aren't they not varying then? Okay, was the they
And
could
that is kind of what my point was as well. I mean, varying them and then see how does the time change, and vary them and say what that means for the precision, right? Because
Yeah.
I can always just choose some very high epsilon, very low delta, or sorry, very high delta and all. And then
But
if I
that
have a
would
very high epsilon
increase
and
your
delta,
increase your running time, right?
yeah, that would decrease my runtime. I'm saying if I choose a very weak epsilon and delta,
Oh,
I
weak
mean
epsilon.
large values. Yeah. So
yeah.
larger values
Here's
are
what
weaker.
I would do. Okay.
Okay.
Why am I getting?
No, echo is on my end because I had to go into loudspeaker because the earphone volume ran out. Just hold on for a second. I'll
Until
just
I
fix
ask the
this.
question.
But you keep talking. I think I'll just mute myself.
Yeah. Is it worth formulating this, Abhinav? Okay.
Yeah.
Because I mean, first I want to check if in the experiment section, do they have any discussion of how they chose the epsilon and delta, and if it has any impact on that choice has any for this particular domain of application. Okay. That I would first check. If once we get clarity on that, then formulate this question and then actually send it to Kuldeep. Okay.
Yeah.
That would be a good follow-up thing to do. Yeah.
Yeah. I'll look into it.
Yes.
I'll
I mean, just formulate that question. I mean,
Okay.
just
Yeah.
as a post-assessment. Okay. Yeah.
Yeah.
So, any other questions for anybody else? Oh, do you have any more slides?
Yeah, that's about it from my side. So
Yeah. What is the future work that they say? Well,
so the like integration with SMT solvers and further optimization of this approx counting, right? That's what they also suggest. And
So what do they mean by integration with SMT solvers? Do they elaborate?
no, not really. But yeah,
I
so
see.
integration would just mean that like there's a one pipeline and like one straight pipeline where you just give your model and you don't need the conversion to do yourself.
No, conversion from a model to pseudo Boolean constraints.
Yeah, correct.
Okay. No, but
Yeah.
I mean, almost all models are in a format which SMT solvers won't be able to read directly, right?
won't be, right? They won't
Yeah.
be able to read. So that's what
Oh, so they're saying,
there's
okay,
an
let's,
integration with them, so that
correct, correct.
there's a way to convert them directly there.
So more
You don't
models
have
is
to think.
basically what they mean. Yeah.
Correct.
Yeah. Okay. So makes sense. Yeah.
Okay. And that's it from my end.
Okay, any other questions for Abhinav? Okay, thank you.
Thank
Yeah,
you.
we'll start at 2:30, the afternoon session, 2:30.
Somebody's saying
Hello,
something.
sir.
Is
Yeah, like,
The-
am I audible?
Yeah, Aritra, yeah, please go ahead. No, you were better.
Actually, am I?
Speak up.
Yeah, am I audible?
Yeah, now you are.
Yeah, am I audible?
Yeah, you are.
Like my network connectivity is very bad, so I'm not sure. So I was figuring out that probably going to say like the LLPXP and subscriber PXP and so I tried to consider up an example. Should I show it or like should Avinav talk about it later like that?
well, like you can show it right now. It's
No, I think
I'll be
you
glad.
should. You should show it right now. I'll
Yeah.
make
Oh,
co-host.
okay.
Yeah.
Then I think I'll just share my
Well,
screen.
less work for me.
Yeah, no problem. Just a minute.
Yeah, go ahead.
Yeah, just a minute. Like I was opening my image. Can you see? Can you see?
Not yet.
But have you stopped sharing, Abhinav?
Yeah, I stopped sharing quite a while ago, but
Okay.
now it's
But I
visible.
still see.
This is Aritra's screen, sir.
Oh, okay.
Yeah.
Yeah, but why am I
Oh,
seeing?
actually, my network connection is pretty bad, so I think that's the reason. Now can you see it?
Yeah.
Yeah.
Yeah. So basically, let's say A, B, C, D are the features, and result is the actual the output of the distance. Okay. So A, B, C, D, all of them can take 4 possible values: 1, 2, 3, 4. Is it fine?
Yeah. This makes sense. Go on.
Yeah. So let's take this classification instance. So 1, 1, 1, 1 results in T, and the other classification instances are like this: 1, 1, 2 is T, 1, 1, 1, 3 is T, and 1, 1, 1, 4 is all false. Okay. So these for these classification instance, like marked in these, this ABC is an explanation, because like we can see 75% of the time the result is true, right? So ABC is definitely a weak PHP. Okay.
Sure. So let's say that the threshold is 50% or something. Yeah.
Yeah.
So-
I
so
treated
what
70%. Like, yeah. Sorry.
Sure. Yeah.
So you're taking 111 as your instance, right?
A comma
Yeah.
B. Yeah. Like this is the classification instance. 1, 1, 1, 1.
Okay.
True. This is
Yeah.
the classification instance. Yeah.
Okay.
So ABC is a weak PXP. Its threshold is 0.7, right?
Yeah.
Now we'll try to consider the example like that. Like if we remove any of them, AB or AC and BC, none of them will be a weak PHP. Okay, we can do that. Like what we can do is like, let's say we remove C. Okay. So now we're trying to prove that AB is not a weak PHP. So we remove C from the ABC set. Now what we can do is like we can set C's value to 2 like this. To classification is like this. So 1121 is false, 1122 is false, 1123 is false, and 1124 is false. Okay, true. Okay. And value of C, like 113, if we go through all possible these, we'll always get true. And if we fix the value of C to 4 and go for all possible values of 4, D, then we'll get all false. Okay. Is that fine? Yeah.
So
Now
can you
if
just
we,
repeat that one? So you're saying that if we
Yeah.
set C to 2, 3, or 4, we'll get the same false, true pattern as you keep changing D. Is that what you're saying? Sorry. Maybe just repeat.
No, if we set C2, then we'll get this.
We'll get this pattern.
Say
Yeah.
50. If
Right.
we set C2 3, then we'll get all true. If we set C2 3, 8, 4, then we'll get all false. Okay.
Okay. Sure.
Then what we can see is like for if A comma B cannot be an explanation, because in the 50% of the case, like 1, 1, 1, 2, there are 3 trues, 1 false, and in this case 3 false, 1 true, and 4 trues, 4 false. So we can say 50% of the cases A comma B was actually an explanation, and 50% cases it was not, right?
Right. Yeah, that
So,
makes
so AB is not an explanation, a weak PXP. Okay, it's fine, right? A comma B is not weak PXP.
Correct.
Is that fine? Okay. Now, similarly, what we can do is like we can fix A comma C to 1 comma 1 and do the same for B, and we can fix B comma C to 1 comma 1 and do the same for A. Then also none of AB, none of BC, none of AC will not be a weak PXP. Okay.
sure. So, but then what we have now is we have a weak PXP ABC such
Huh?
that no subset is a weak PXP, right? But we
No,
yeah.
locally minimal. It's locally minimal, but we'll try to construct such that A is itself a weak PXP. A is itself a weak
Okay,
PXP.
okay.
So
Okay.
then A will be a
Right, sure. Go
and
ahead.
then ABC will be locally minimal but not subset minimal. Okay, so
Yeah.
this part should be easy, and I hope I'm not wrong in this case. But what we can do is like we only use the cases where B comma C is 1 1 1 2 1 3 or 3 1, 1 3 or 1 4, and the case 1 1 2 1 3 1 and 4 1, right? Okay, so let's say
I didn't understand this
let's say
last
we fix, I'll explain it. So now what we can do is what we'll do is we'll fix A and go through all possible values of B comma C comma D, right? Is that fine?
Yeah.
Yeah. So now what we only is block the value of, like we while constructing we only block the value of 1 1 B comma C is 1 1 or 1 2 or 1 3 or 1 4, like in this case
Correct,
1 2 we
correct. Yeah,
blocked 1 2
those are
we
already
blocked 1.
taken. Yeah.
Yeah. Similarly for B, like when we removed A, so we blocked 2 1 3 1 4 1 also, right?
Mm-hmm.
Now the remaining parts are like we haven't used the value B comma C of like value of 2 comma 2 2 comma 3 2 comma 4 3 comma 2 3 comma 4. A lot of them are remaining, right? So we
Right.
can set all of them to true, and the probability will just burst up, like, right?
Right.
Is the point
Right.
clear?
Right.
So
Right.
now
Yeah. Yeah.
A
Yeah.
will
Yeah. Yeah.
A will
Makes sense. Yeah, that's what. That's
like
what.
I
Yeah. Yeah.
can't like
Yeah,
like
that's what I
that's the point.
guess.
Like we can
Yeah, I
actually
think you've given the example, which is what Abhinav was probably getting at. Okay, so the other things that
So basically, if we allow ourselves to change, I mean, there's enough space in the.
exactly, that's the point. Like if we make the set bigger and bigger, like this value space bigger and bigger, then the more chance of this happening. Like the locally minimal PXP is not equal to subset minimal PXP.
Correct.
Yeah.
And then, I mean, I don't know if that means anything. I mean, so the one question that I had
Yeah.
during the AXP, the original, not this one, the GuyCats paper. There, there's this question we had. We were classifying something as a boot, and okay, so if the AXP is indeed the silhouette of the boot, then does that mean that if we set everything in the outside to blue, is it still going to be classified as a blue? That does mean that does that mean that
Exactly.
yeah, so it's a similar kind of a thing. Question can be asked here as well, right? I mean, if you're saying that okay, if you fix these things for a weak XP, if you fix these things and you set anything else to something, some whatever, then with high probability I'll get this thing. Does that mean that? Yeah, I think that is actually this is actually slightly better than that, right? Because then that doesn't mean that I'll get a boot when I set it to all blue. It just that means the probability of that is going to be high, which
Yeah.
is still fine
So
because I mean I
yeah.
can take
Yeah.
such really bad corner cases and that will hide within the probability in some sense.
yeah. Okay. Yeah, I think
That's even better, right? Because if
yeah,
we
this
even
is
have like
just yeah, the rest of you, if you want to go for lunch, it's okay. So this is yeah.
Diganta.
Yeah, that's even better,
Still
right?
better because if we have bit flips at the boundary points, like it still classifies it correctly, like with
Yeah,
high
yeah,
probability,
yeah.
right?
Yeah. So it somehow takes into account a lot of like